The Big Bang Theory has reigned as the ultimate explanation of how everything began nearly 14 billion years ago. But then came the James Webb Space Telescope, humanity's most powerful eye on the heavens, a machine capable of peering back to the universe's earliest moments. What it revealed left scientists in shock. Galaxies that should not exist, structures that appeared far too early, and cosmic patterns that seemed to defy the very foundations of the Big Bang. Could it be that our most trusted origin story is wrong? Could Webb be rewriting the greatest chapter of cosmic history right before our eyes? Before we start the video, tell us where in the world you're watching from and what time it is for you right now. Drop it in the comments below and prepare for a fascinating journey as we uncover what James Webb recently discovered. For countless years, ever since human beings first raised their eyes to the stars, we have wanted to look farther and farther into the depths of space. It was never enough just to see the shining stars above us. We wanted to go beyond them, beyond the Milky Way, beyond the countless galaxies, and to somehow peer back in time to see where it all began. Scientists especially have been driven by this hunger, because they believe that hidden in the most ancient light of the universe lies a clue to the beginning of everything. They imagined that, if we could look deeply enough, we would see a faint signal, the very first flicker from the time when all of creation began. That light, they thought, would tell us how the universe was born and how it grew into what we see around us today. For most of the last century, there was one explanation that stood above all others. It was called the Big Bang Theory. According to this idea, the universe began nearly 14 billion years ago, in a moment so strange and powerful that it could hardly be put into words. Everything we know, every star, every planet, every grain of dust, and even space and time themselves, sprang out of something unimaginably small and dense, a single point called a singularity. In the blink of an eye, that tiny point grew, stretched, and expanded into a universe that has been swelling outward ever since. From that moment onward, galaxies, stars, planets, and eventually living beings like us all became part of this great outward flow. The Big Bang was not just a scientific theory. It was a story about beginnings, and it became the most widely accepted story in modern astronomy. The Hubble Space Telescope, launched in the year 1990, gave us pictures that seemed to confirm this tale. It looked deep into the heavens and showed us that the universe really was expanding, that galaxies were moving away from us, and that everything we thought we understood about cosmic history was correct. For decades, Hubble's photographs filled books, documentaries, and classrooms. They seemed to reassure scientists that the Big Bang Theory had been right all along. But then, a new telescope arrived, one that would challenge everything we thought we knew. This new instrument was called the James Webb Space Telescope, or JWST for short. Unlike Hubble, it was not created simply to sharpen our view of the universe, or to polish up old ideas. No, James Webb was built to look deeper and further back in time than any telescope before it. Its purpose was nothing less than to catch the faint glow of the very first galaxies, to gaze upon the cosmic dawn, that sacred moment when the first stars lit up the dark universe. The creation of James Webb was itself a monumental journey. It took decades of planning, testing, and rebuilding. It required the efforts of thousands of engineers, scientists, and dreamers. The cost of this telescope rose to nearly $10 billion, making it the most expensive and ambitious observatory humanity had ever created. But people kept working, because they knew that if it succeeded, it would be worth every bit of effort. Finally, in December of the year 2021, after so many delays and struggles, the James Webb Space Telescope was launched into space. Its golden mirror, with 18 hexagonal pieces fitted together like a jewel, unfolded far away from Earth. It promised to open a new chapter in our understanding of the universe. What few people expected, however, was that it might also close the chapter we thought was already settled. When the first pictures from James Webb were released in the middle of the year 2022, scientists and the general public alike were struck silent. The images were beautiful beyond belief. They showed fields of galaxies glowing like jewels scattered across the black canvas of space. They showed stars wrapped in clouds of gas, brilliant explosions of light, and details no human eye had ever seen before. Yet beauty was only the beginning. Beneath that breathtaking golden glow, hidden in the data, were mysteries and contradictions that shook the scientific world. For decades, the Big Bang model had painted a picture of what the earliest galaxies should look like. They were supposed to be small, chaotic, and poorly formed, more like cosmic toddlers just learning to walk. The galaxies of those early times were expected to be fragile, uneven, and unstable. But what James Webb revealed was completely different. The galaxies it found in the earliest epochs of the universe were not clumsy infants at all. They were too big, too smooth, and sometimes even too old. They looked like fully grown adults standing where we thought we would find newborn children. It was as if the universe had skipped its early, awkward years and appeared ready-made, organised and complex from the very beginning. What startled scientists even more was not only what James Webb saw, but when it saw it. The models that guide modern cosmology predicted that the first galaxies should have taken hundreds of millions of years to form after the Big Bang. That made sense according to the old story. First came the explosion, then came a long dark age where gas cooled, and only after a long wait did the first stars ignite. But James Webb found galaxies shining brightly only a couple of 100 million years after the supposed beginning of time. In cosmic terms, that is like finding a mature tree just a few weeks after planting a seed. According to current theories, this should have been impossible, and these galaxies were not faint little clusters of light. They were massive, filled with stars, gas, and heavy elements that were not supposed to exist so early. They were already rich and complex. This was not just one surprising find either. As more and more data came in, the same story kept repeating. Too many galaxies appearing too soon, growing too large and looking too organised. The pattern was undeniable. The evidence was piling up, and this evidence did not fit the Big Bang picture. It was not just a small mistake that could be patched up by adjusting a few numbers. It was not a minor detail that could be explained away in a footnote. No, this was the kind of problem that shakes the foundation of the entire model. One astrophysicist put it bluntly: these galaxies should not exist. Another scientist used a vivid image, comparing the discovery to walking into a classroom where you expected to see toddlers, but instead found it filled with fully grown adults. This was not the picture of a young, turbulent universe just beginning to take shape. It was the picture of a universe that already looked mature, even near its supposed birth. So the great question rises, what did we miss? Did we misunderstand the stretching of light, known as redshift, which scientists use to measure distance and time in the universe? Could it be that our way of reading cosmic history is flawed, like trying to read a book in a language we do not fully understand? Or perhaps time itself on a cosmic scale is stranger than we imagine, tricking us into thinking events happened sooner or later than they really did. Some scientists have even begun to whisper the most unsettling idea of all. Maybe the very notion of a universe that began with a singular event is wrong. If that were true, the consequences would be enormous. For generations, the Big Bang theory has stood as the guiding framework of cosmology. It has shaped how we think about time, matter, and our place in the cosmos. If James Webb's data keeps showing structure and complexity where there should be none, then the Big Bang might not just need a little fixing, it might need to be replaced altogether. That does not mean the universe had no beginning. But it might mean that the beginning was not what we thought. Maybe the universe did not burst into existence from nothing. Maybe it always existed in some form. Or perhaps it is part of a grand cycle, expanding and contracting, dying and being reborn over and over again. Such ideas, once dismissed as fringe, are now quietly being spoken about in serious scientific circles. There is no doubt that James Webb has already changed everything. Not because it has proven the Big Bang false beyond all doubt, but because it has shown us truths we did not expect. And that is the heart of science. To be surprised by reality, to find that the universe is not what we imagined, but something far more mysterious and wondrous. At the end of the day, opinions, theories, and models are only human attempts to explain what is out there. The universe itself does not care what we think. It simply is what it is. And now, thanks to James Webb, we can see it more clearly, more deeply, and more beautifully than ever before. The James Webb Space Telescope was built with one bold purpose in mind: to see the universe in a way that no telescope before it ever could. People sometimes think of it as just a newer and bigger version of the Hubble Space Telescope, but that is not correct at all. Hubble and Webb are like two artists painting with completely different palettes. Hubble worked mostly with visible light. the kind of light that our own eyes can see, and also with ultraviolet light, which is light with shorter and more energetic wavelengths. Webb, however, was designed to look at the universe in infrared light, which is light that our eyes cannot see, but that carries a very special kind of information. This difference might sound small and technical, but it changes everything. It is the reason why Webb can show us things that Hubble never had the power to reveal. To understand why infrared light is so important, we have to think about how the universe itself has changed since the beginning. According to the leading theories, the universe began almost 14 billion years ago in a sudden explosion of energy and matter that scientists call the Big Bang. Ever since that moment, the universe has been stretching and expanding like dough rising in an oven. When light travels across such a universe, the very fabric of space pulls at it and stretches it out. What began as bright and powerful light slowly becomes weaker and redder the farther it travels. This stretching is what scientists call redshift. The light from the first stars and galaxies has been travelling for billions of years, and during that journey it has been stretched so much that it no longer shines in the visible part of the spectrum. By the time it reaches us, it glows only in the infrared. That means if we want to see the first galaxies, we cannot use a telescope that looks in visible light. We need one that can look deep into the cold glow of the past, one that can capture these ancient whispers of light. That is exactly what the James Webb Space Telescope was built to do. Webb is not parked in a simple orbit around the Earth the way Hubble was. Instead, it sits nearly 1 million miles away from our planet, at a very special spot called the second Lagrange point, or L2. This is a place where the gravity of the Earth and the gravity of the Sun balance out in such a way that a spacecraft can stay almost perfectly still with very little effort. From this quiet perch, Webb hides behind a huge heat shield that is as wide as a tennis court and made of 5 delicate layers. This shield keeps the telescope in permanent shadow, safe from the burning rays of the Sun, the reflected glow of the Earth, and even the faint shine of the Moon. Out there, Webb operates in near-perfect darkness, its mirrors and instruments cooled until they are colder than the icy surface of Pluto. In such a frozen state, it becomes sensitive enough to pick up the faintest glimmers of light that have travelled across more than 13 billion years of cosmic history. It is often said that Webb is a time machine, and in this case the phrase is not just a poetic metaphor, it is literal. Because light takes time to travel, when Webb looks farther into space, it is also looking further into the past. Every faint red glow it captures comes from a moment when the universe was younger. The telescope was not only built to look farther away than any other observatory, but also to look back to the very first moments when the cosmos began to shine. One of its main missions was to study something scientists call the cosmic dawn. This was the age after the so-called Dark Ages, a time that followed the Big Bang. During the Dark Ages, the universe was filled with hydrogen gas that was still too cool and too dark to glow. Atoms had formed, but stars had not yet been born. Then, at last, the first stars ignited, burning hydrogen and helium in their cores and filling the universe with light for the very first time. Scientists built Webb hoping it would catch these earliest flickers of starlight, the sparks that turned a cold, dark cosmos into a luminous one. In their expectations, they pictured Webb seeing galaxies in the act of being born. Small clumps of stars held together by weak gravity, irregular in shape, unstable, chaotic, and primitive. These baby galaxies would be made mostly of hydrogen and helium, with almost no heavy elements, since heavy elements like carbon, oxygen, or iron are created only after many generations of stars have lived and died. The telescope was supposed to show us how structure grew slowly over billions of years, how galaxies merged, how stars forged new elements, and how the simple became complex. Webb was not just built for one purpose, though. Its wide golden mirror, 6.5 meters across and coated with thin layers of real gold, was designed to do many things. It could study how galaxies change and grow, how stars are born inside thick clouds of gas and dust, and even how planets around distant stars might have atmospheres. That mirror is more than 2.5 times wider than Hubble's, which means Webb can gather far more light. With more light comes more detail, sharper vision, and the ability to see fainter objects than ever before. For scientists, Webb was the ultimate tool to confirm their ideas about the universe. They believed that if they looked far enough back in time, they would see the early chaos that their models predicted. When Webb finally unfolded in space and sent its first images home, the world gasped. The pictures were stunning, glittering galaxies scattered like jewels across endless blackness, vast clouds of dust glowing like paintings, and delicate structures shaped by forces beyond imagination. But behind the beauty of these pictures was something even more powerful: the data, the measurements, the details that scientists could read like a secret code. And what that code revealed shook the scientific community to its core. Webb did not show small, messy galaxies just beginning to form. Instead, it revealed massive galaxies, well-shaped and organised, existing astonishingly close to what should have been the beginning of time. It found stars that contained heavy elements, even though such elements should not have had time to form. It showed galaxies that looked mature and stable, when the universe was still only a tiny fraction of its current age. What scientists expected to find, chaos slowly turning into order, was not what they saw. What they actually saw looked more like a universe that built itself far faster, far earlier, and in far more complex ways than anyone had believed possible. This was not a small error that could be explained away by saying Webb's instruments were not working properly. The telescope performed perfectly. Its mirrors aligned flawlessly. Its detectors picked up even the faintest light, and its instruments like NIRCam and NIRSpec returned clear and complete views. The problem was not with the telescope. The problem was with the assumptions. Webb had been designed to confirm the Big Bang model in greater detail, but instead its discoveries began to raise new doubts about whether the model was complete, or whether our understanding of the timeline of cosmic evolution might be deeply flawed. What scientists had long believed was a slow process, galaxies forming over hundreds of millions of years, now appeared to have happened almost instantly, as if the universe had raced ahead in its first stages. The timeline seemed shorter, the structures more mature, and the stars richer in heavy elements. This was not what the models predicted. The more Webb looked, the more unsettling the evidence became, and yet Webb was doing exactly what it had been meant to do. It was revealing the truth, even if that truth did not fit into our neat theories. By looking into space, Webb was also forcing us to look into ourselves, into our assumptions, into the stories we have told about the beginning of everything. Its golden mirror, shining in the cold of deep space, was like a cosmic teacher, showing us that knowledge is never finished, and that sometimes the most advanced tools lead us not to answers, but to deeper, more difficult questions. When humanity built Webb, we thought we were building a machine that would confirm what we already believed. But in reality, we built a machine that may have begun to rewrite the story of the cosmos. Its discoveries remind us that the universe is not a puzzle already solved. It is a mystery still unfolding, and every new glimpse into its depths reveals how much more we have to learn. To really grasp why the discoveries of the James Webb Space Telescope have shaken so many scientists, we first need to go back and carefully think about the very theory that it seems to be challenging. The theory in question is the famous Big Bang theory, a phrase that nearly everyone has heard at one time or another. It appears in countless documentaries, in popular science books, in classrooms, in news articles, and even in casual conversations. Yet because it has been repeated so often, in so many different ways, its true meaning has become blurred, twisted, or simplified into something quite different from what scientists originally intended. When most people imagine the Big Bang, they picture an enormous explosion, a colossal cosmic blast that sent stars, planets, dust, and all the galaxies flying outward into empty space. It is an image of a bomb going off in the sky, scattering matter like shrapnel into the blackness. This is a powerful picture, but it is not really what the theory is saying. The Big Bang was not an explosion inside of space. It was not as if there was already a stage or a background called space, and then the universe detonated within it. Instead, the Big Bang was space itself bursting forth. It was the expansion of space, time, and energy all together. What the Big Bang theory actually describes is a mathematical model of how the universe has been expanding. According to this model, around 13.8 billion years ago, everything that would ever exist, space, time, matter, and energy, was concentrated in a state of unimaginable density and heat. This was not a point located somewhere in space, because there was no space in which it could sit. It was space itself that was compressed to nearly zero volume. Then something extraordinary happened. space began to stretch. It did not expand into something else because there was no outside to expand into. Instead, the very fabric of reality began to stretch and grow, carrying everything with it. This expansion has never stopped. It is still going on right now. Galaxies are not flying through pre-existing space like sparks shooting out from a fire. Instead, they are being carried apart by the stretching of space itself, the way raisins in bread dough move away from one another as the dough rises. This remarkable picture was not based only on imagination. There was evidence, strong, convincing evidence that supported it. The first major clue came in the year 1929, when a man named Edwin Hubble, working at the Mount Wilson Observatory in California, made an astonishing observation. Hubble noticed that light from distant galaxies was shifted toward the red end of the spectrum. This redshift meant that the light waves were being stretched into longer wavelengths, and the only explanation was that the galaxies themselves were moving away from us. The universe was getting bigger. If galaxies were drifting apart now, then long ago they must have been closer together. If you keep tracing the motion backward, you eventually reach a time when everything was packed together in one incredibly dense, hot state. In the language of mathematics, this backward tracing points to a singularity, a place where equations break down and known laws of physics no longer apply. The idea took hold, and in the decades that followed, more and more pieces of evidence were discovered that fit the model. In the year 1964, two researchers, Arno Penzias and Robert Wilson, stumbled upon something they had not expected while working with a radio antenna. They detected a faint background hum, a glow of microwave light coming evenly from all directions in space. At first, they thought it might be some kind of interference or even pigeon droppings in their equipment, but soon they realized they had found something astonishing. This glow, now called the cosmic microwave background radiation, was exactly what supporters of the Big Bang had predicted years before. It was the cooled down remnant of the blisteringly hot early universe. Other discoveries followed. Scientists measured the amounts of the lightest elements, hydrogen, helium, lithium, that filled the cosmos. The proportions matched perfectly what one would expect if those elements had been forged in the fiery first minutes after the Big Bang, when nuclear fusion would have taken place in the young hot universe. Step by step, the evidence built up. From these clues, a grand story unfolded. The universe was born in fire, expanding and cooling as time passed. Over billions of years, matter clumped together under gravity, forming stars, then galaxies, then clusters of galaxies, and eventually planets and life itself. The framework was so successful, so persuasive, that it became the standard cosmology taught in every textbook and used in every scientific simulation. Scientists across the world accepted it as the best explanation for the origin and evolution of the universe. Yet even as the theory triumphed, questions remained. There were gaps that did not fit neatly into the picture. One puzzle was called the horizon problem. The cosmic microwave background looked astonishingly uniform, the same temperature in every direction. But parts of the universe that now appear similar were, in the early days, so far apart that there had not been enough time for light or energy to travel between them. How could they have coordinated their properties so perfectly? Another puzzle was called the flatness problem. Measurements showed that the universe's shape is astonishingly close to flat, like a sheet of paper rather than a ball or a saddle. Why should that be? A third issue, the monopole problem, asked why we do not see certain exotic high-energy relics that should have been produced if the universe had started in the way we think it did. To deal with these puzzles, cosmologists in the 1980s came up with a bold new idea known as cosmic inflation. This concept proposed that in the tiniest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, growing exponentially faster than the speed of light. This sudden burst of growth would have stretched the universe smooth and flat, ironed out irregularities, and diluted away the unwanted relics. It explained the horizon, the flatness, and the missing monopoles in one sweep. Inflation was not part of the original Big Bang theory, but it soon became attached to it, like a necessary upgrade. In modern discussions, when people talk about the Big Bang, they usually mean this combined picture: an initial singularity, a brief period of inflation, followed by slower expansion, cooling, the formation of atoms, the release of the cosmic microwave background, and finally the growth of stars and galaxies. But even this improved theory has boundaries. It does not tell us why the universe began. It does not describe what came before, because in the traditional understanding, time itself began with the Big Bang. Asking what happened before is like asking what lies north of the North Pole. The theory also struggles to say much about the true nature of the singularity itself. At that point, our current equations collapse. General relativity, which governs gravity, fails to predict, while quantum mechanics, which governs the smallest scales, takes over. We do not yet have a theory that unifies the two. This is the stage on which the James Webb Space Telescope entered. The Big Bang framework paints a clear timeline. The universe begins hot and chaotic, then slowly cools and develops structure. Galaxies should emerge gradually, stars should form through no nuclear processes, and everything should align neatly with the ages calculated from the cosmic microwave background and the redshifts measured by astronomers. But Webb's keen eye is showing something strange. Galaxies are appearing that seem too massive, too developed, too well organised for such an early era. If these galaxies really are as old and as large as they appear, then the carefully constructed timeline may be off. If the timeline is off, then perhaps the link between redshift, distance and age is not as firm as we thought. And if those foundations shake, then our estimates of the universe's age, or even the rate at which it is expanding, might need to be rewritten. The unsettling possibility is that our entire understanding of space, time and light may be incomplete. The Big Bang theory gave us a stable foundation, a model that seemed to tie together observation and mathematics beautifully. But science is not about comfort, it is about truth. And if Webb's discoveries suggest that the universe is more complicated, stranger and older than we believed, then the model itself may need to evolve. For many years, long before the James Webb Space Telescope stunned the world with its first images, astronomers already had hints that something was not quite right with the universe. They had an uneasy feeling that galaxies, those grand cities of stars scattered across the cosmos, were not behaving in the neat, orderly way that their theories suggested they should. It was not James Webb that first opened the door to this mystery. The cracks in the story began decades earlier, with another telescope, one that was already legendary in its own right, the Hubble Space Telescope. In the middle of the 1990s, the Hubble Space Telescope had been circling Earth for several years, sending back breathtaking pictures of planets, nebulae, and distant galaxies. But in the year 1995, a bold idea was put forward, an idea that seemed almost foolish at the time. Some astronomers decided to point Hubble at a part of the sky that looked completely empty. This was not a patch filled with bright stars, colourful gas clouds, or obvious galaxies. It was simply a small square of darkness, a tiny black window in the night. Most people, even other scientists, thought nothing would come of it. After all, why waste precious observing time on emptiness? But this was no ordinary attempt. The astronomers kept the telescope's shutter open, not for minutes or even hours, but for 10 straight days. Imagine that. 10 full days of patiently gathering the faintest whispers of light from the deep, deep past. When the images were finally processed and revealed, the world of astronomy changed forever. What had looked like nothing turned out to be overflowing with something. The blackness of space was suddenly alive with thousands upon thousands of galaxies, each one a sprawling collection of billions of stars. Every tiny smudge, every faint spiral or blurry arc of light was a galaxy unimaginably far away. Some of them were more than 10 billion light-years distant. That meant the light had been travelling across the universe for over 10 billion years before finally reaching the mirror of Hubble. In other words, astronomers were not just looking far into space. They were looking far back in time, seeing these galaxies as they had existed near the very dawn of creation itself. This single image, which became famous as the Hubble Deep Field, was nothing short of a revelation. It proved in one breathtaking moment that the universe was far more crowded with galaxies than anyone had ever dreamed. What had once seemed empty and lifeless was now revealed to be full to the brim with cosmic cities. It also proved another idea that astronomers had only hoped for. By looking deeper into space, you could indeed look further back in time, catching glimpses of the earlier stages of the universe's story. Hubble's success with this daring project encouraged astronomers to push further. Again and again, they returned to the idea of staring at apparently blank patches of sky for days or even weeks, stacking exposures and squeezing faint photons out of the darkness. Over the years, Hubble produced the ultra-deep field, and later the extreme deep field. each one peeling back another layer of the universe's past. These pictures stretched the telescope's abilities closer and closer to the very limits of what human eyes, or human technology, could possibly see. Yet with every improvement in resolution, with every increase in sensitivity, something unsettling began to creep into the story. The galaxies appearing in these deep fields were not quite what scientists had expected. According to the reigning model of the universe, the Big Bang theory, galaxies in the early cosmos should have looked chaotic, clumpy, and primitive. They were supposed to be messy swarms of young stars still in the process of settling into shape, but that was not what Hubble showed. Instead, sprinkled among the expected irregular blobs, astronomers saw galaxies that looked far too organised, far too mature for their apparent age. Some of them had well-formed spiral arms, others had bright, bulging centres, some even showed hints of orderly rotation, as if they had already had billions of years to settle into balance. Yet, according to their redshifts, the stretching of their light caused by the expansion of the universe, these galaxies were supposed to have existed just a few 100 million years after the Big Bang. In cosmic terms, that was like finding a full-grown tree in a field where only tiny saplings should exist. At first, many scientists brushed these oddities aside. They said perhaps the galaxies were being misclassified. Maybe the light was being distorted by gravitational lensing, the bending of light by massive objects lying between us and them. Or maybe these strange examples were simply rare exceptions, little flukes that did not threaten the larger picture. But the uneasy feeling did not fade. Instead, as more and more studies were carried out, the same troubling pattern kept appearing. Galaxies were showing up too early. Stars inside them seemed to contain heavier elements, what astronomers call metals, at levels that should have been impossible so soon after the Big Bang. Black holes at their centres appeared far too massive for their supposed age. Each new discovery added another crack to the elegant framework of the Big Bang model. To understand why this was so disturbing, it helps to know how the timeline of the universe was supposed to unfold. According to the standard Big Bang picture, after the great explosion of creation, the universe was filled with nothing but hot expanding gas. It took hundreds of millions of years for gravity to gather this gas into the first stars. Those stars would then live, burn, and eventually explode as supernovae, scattering heavier elements into the cosmos. Only after several cycles of this process could galaxies form with stable structures, rich chemical contents, and supermassive black holes at their hearts. That was the theory. The early universe should have been poor in metals and messy in structure. But Hubble's deep fields seemed to show something else entirely. There were galaxies that were not primitive but already enriched, already spinning, already mature. It was as if the universe had rushed through its adolescence at a pace no one thought possible. One of the clearest examples of this unsettling reality came from a galaxy that astronomers labelled GNZ 11. Hubble detected this faint, distant smudge of light, and later spectroscopy confirmed its distance. It was seen as it had been only about 400 million years after the Big Bang, a blink of an eye in cosmic history. Yet GNZ 11 was enormous, with a mass equal to 1 billion suns. Even more astonishing, it was actively forming stars at a furious rate, far beyond what the models predicted was possible at that time. This galaxy was not just surviving in the infant universe, it was thriving and growing at breathtaking speed. Still, many scientists urged caution. Hubble, as powerful as it was, had its limitations. The further it looked, the harder it became to distinguish faint galaxies from background noise. And while it could see far into space, its infrared sensitivity, the ability to detect the stretched-out light from the earliest galaxies, was not strong enough to answer all questions. If humanity wanted to truly peer into the first moments of cosmic history, something more was needed. A new kind of eye, sharper, deeper, and tuned specifically for the faint glow of the young universe. That eye would eventually arrive in the form of the James Webb Space Telescope. But here is the key point. When James Webb finally began sending back its jaw-dropping images, its discoveries did not come out of nowhere. The clues had already been planted years earlier in the deep field pictures of Hubble. The whispers of trouble were already in the data. The signs were already there. Galaxies that seemed to be growing up too quickly, stars forming in places where they should not have, and black holes accumulating mass far faster than anyone thought possible. This is how science often works. At first, when something strange appears, it is ignored or explained away. Then it is investigated more closely. Sometimes the oddities can be folded into the existing model with small adjustments, but sometimes, when enough of them pile up and refuse to be explained, the model itself begins to crack. Slowly, reluctantly, scientists are forced to consider that their picture of reality might not be the final word after all. What started as a single astonishing photograph in 1995, a simple act of pointing Hubble at an empty square of sky, may one day be remembered as the beginning of a much larger story. Those faint smudges of light, those galaxies that seem too mature for their age, might be the first cracks forming in the foundation of the Big Bang Theory itself. And now, with James Webb revealing even more shocking details, those cracks are spreading wider, demanding that science rethink one of its most cherished ideas. When the James Webb Space Telescope was launched, and finally opened its golden mirrors to the universe, astronomers expected beauty, and they certainly got it. The pictures that came back were breathtaking, some of the most astonishing views humanity had ever seen of the deep cosmos. Yet along with the beauty came a shock so great that it began to shake the very foundations of how we understand time itself on the cosmic scale. The telescope did not just show us stars and galaxies, it showed us a puzzle that made many scientists pause in disbelief. The universe, it seemed, was not following the carefully written script that decades of textbooks had taught us. For a long time, the story of galaxies was thought to be simple in outline, even if complex in detail. After the beginning of the universe, which according to the Big Bang Theory happened around 13.5 billion years ago, there was first a period of chaos, then gradual order. Atoms had to form out of the hot soup of plasma. Then clouds of gas had to come together under the gentle pull of gravity. Those clouds had to cool down, collapse, and finally give birth to the first stars. Stars would live, die, and scatter heavier elements into space. More stars would form, mixing those new elements into their cores. Then, slowly, galaxies would grow, assembling themselves piece by piece like enormous cosmic cities under construction. All of this, scientists believed, required billions of years. In this story, the young universe was messy, slow, and unorganized. But what James Webb revealed was a completely different scene. Instead of a nursery full of infants just starting their lives, Webb showed us something closer to an exhibition hall of fully grown adults, walking around as if they had always been there. Within only a few 100 million years of the supposed beginning, galaxies were not just present but already large, massive, and well organized. They had the shapes of spirals, with bulges and arms. They had heavy elements. They had the kind of complexity one would expect only after long stretches of time. It was not one or two isolated examples which could perhaps be dismissed as lucky accidents. There were too many of them. Within only weeks of Webb's first deep-field images being released to the public, astronomers began noticing the same thing again and again. Galaxies that looked too old, too big, too mature for their place in cosmic time. According to the traditional model of the Big Bang, such objects should not exist that early. They should have been small, irregular clumps of gas just beginning to take shape. Instead, Webb was finding systems whose stellar masses rivaled that of our own Milky Way galaxy, which itself took billions of years to form, and Webb was finding them at only 300 to 400 million years after the start of the universe's clock. That is an unbelievably short time on cosmic scales. Think of the universe as a human life stretched over 100 years. 300 million years would be like the first few months of infancy. But in that cosmic baby photo, Webb was already seeing skyscrapers, highways, and cities fully built. It was as if archaeologists dug into the ground expecting to find the broken bones of early humans, and instead uncovered fully built skyscrapers from a time when humans were not even supposed to exist. The order of things seemed wrong. One of the first detailed studies that raised alarm was led by Dr. Jan Kartali. His team looked carefully at early James Webb data and measured the redshifts of dozens of galaxies. A redshift is a way of telling how far away and how old something is, because light stretches as it travels through the expanding universe. The greater the redshift, the further back in time we are looking. Kartali's team found galaxies with redshifts higher than 10, which means they were shining when the universe was less than 500 million years old. And these galaxies were not tiny puffs of gas. They were enormous and bright, with signs of chemical richness and defined structures. Some even seemed to have bulges and arms, the kind of architecture we expect in galaxies like our own. They looked not like babies. but like survivors from a much older past. This finding did not fit the math that underpins the Big Bang model. The rules say that atoms need time to form after the explosion, gas clouds need time to collapse, stars need time to live and die. Heavy elements like carbon, oxygen and iron need multiple generations of stars before they appear in abundance. Galaxies are supposed to be the final result of this long process. Yet Webb was showing us galaxies that seemed to skip the queue, as if the universe had fast-forwarded billions of years in only a few 100 million. To make galaxies of that size so early would require something extraordinary. Either stars had to form much faster than expected, or matter had to gather itself into galaxies in ways we do not yet understand, or, even more dramatically, the entire timeline of the early universe would need to be rethought. And the numbers did not add up. The rate at which gas can collapse, the speed at which stars can form, the limits set by physics on how quickly these processes happen, all of it suggested that such massive galaxies could not appear so soon. Some scientists tried to adjust the models. Maybe star formation in the early universe was much more efficient. Perhaps clouds of gas turned into stars almost immediately and at a rate far above what we see today. But that explanation created another problem. The faster stars form, the more radiation they release, and the more supernova explosions occur. That feedback heats up the surrounding gas and actually slows down further star formation. So making stars more efficient only works up to a point before it begins to choke itself off. Others suggested maybe the redshifts were being miscalculated. Maybe these galaxies were not really as old as they looked. But then came the spectroscopic confirmations, which measure light more precisely and act as a gold standard in astronomy. The spectroscopic data agreed. The galaxies really were that far away, and therefore that old. There was no mistake in the measurements. The weight of evidence began to sink in. This was not an illusion or a trick of the telescope. The early universe was far more organised than expected, and it was filled with big, heavy galaxies at a time when there should have been only scattered fragments. This was not just one or two strange cases, it was a whole population. The statistics themselves were undeniable. The implications were unsettling. If galaxies were forming this quickly, maybe our understanding of cosmic time itself was flawed. Could it be that time in the early universe passed differently than we think? Or could it be that the way we connect redshift with distance and age is not quite as reliable as we assumed? That would shake one of the fundamental pillars of modern cosmology, because redshift is the primary tool we use to measure the age of the universe. If it were wrong or incomplete, our entire map of cosmic history would need to be redrawn. And if galaxies formed so quickly, what does that mean for everything else? Our theories of how structure forms in the cosmos rely on the slow accumulation of matter, on dark matter shaping gravitational wells, on feedback processes that regulate star formation. If those processes can leapfrog billions of years of expected time, then the physics may not be what we think. It would be like finding that ancient fossils from the Bronze Age contained skyscrapers and cars. Something fundamental about the order of history would have to be reconsidered. For decades, the Big Bang theory has been more than just a scientific model. It has been a kind of cosmic origin story told in the language of mathematics and light. It promised a narrative where everything begins in simplicity, a hot, glowing plasma, and slowly builds into complexity. Atoms, stars, galaxies, planets, life, and eventually humans. The appeal of this story has been enormous. It explains so much with such elegance. But the James Webb Telescope is now raising doubts about the pacing of that story. Perhaps the script is not wrong, but the timing is badly off. Or perhaps the entire story is incomplete, with key chapters missing or misunderstood. And the truth is, we are only at the beginning of this revelation. James Webb will continue to look deeper and with greater precision in the coming years. Its spectroscopy will sharpen, its imaging will refine, and its surveys will dig deeper into the past. Either these anomalies will be confirmed again and again, growing into a crisis for cosmology, or some new understanding will emerge that resolves the tension. But one thing is certain, the tension is building, and the questions are only multiplying. The discovery of too many mature galaxies too soon is not just a footnote in astronomy. It is a challenge to the very foundations of how we think about the universe. Are we missing some hidden physical law that accelerates cosmic growth? Is dark matter behaving in ways we never imagined? Is time itself in the early universe different from what our equations predict? Or is the Big Bang theory, as central as it has been, due for a radical rewrite. These are not small questions. They touch the deepest parts of human curiosity, where we come from, how everything began, and what rules govern the grand story of existence. The James Webb Space Telescope was built to uncover the universe's secrets, and it has already begun to do so in ways no one fully anticipated. Instead of confirming our neat, comfortable timelines, it has opened a door into a universe that seems to have been in a hurry, a universe that may be far stranger than we ever dreamed. And as we look deeper, we may find that our place in the cosmic story is very different from the one we thought we knew. When astronomers first turned the James Webb Space Telescope toward the distant edges of the cosmos, they expected to witness a kind of cosmic childhood. The common belief was that these earlier snapshots of the universe would reveal only small, scattered and chaotic collections of stars and gas. The picture in their minds was of rough sketches, tiny clumps of material still struggling to come together, waiting for billions upon billions of years to mature into the grand spirals and massive elliptical galaxies that we see around us today. But what they actually saw was not the scattered beginnings of galaxies. Instead, what appeared on Webb's mirrors were objects that seemed far too large, far too mature, and far too well organized to belong to such an early era of cosmic history. These galaxies were not rare outliers. They were not mistakes hiding in the data. They were everywhere, scattered across Webb's deep fields, and they stood as direct challenges to the story scientists had carefully constructed about how the universe was supposed to grow and change. The trouble with these discoveries comes from the fact that in our current way of thinking, the universe has a certain rhythm and pace. Everything forms step by step, in a process that takes an immense amount of time. According to the standard story, galaxies do not simply appear in their finished form. They begin small, just faint clumps of matter in the young universe. Then, across billions upon billions of years, they gather more mass, merge with one another, and undergo bursts of star formation, until they become the magnificent structures we admire today. This process, sometimes called the hierarchical model, is deeply tied into our understanding of the Big Bang and the physics that followed it. It tells us that small things join together to make larger things, and it paints a picture of cosmic growth that is patient and gradual. But James Webb did not find patience and gradual growth in those first glimpses of the distant past. It found galaxies that seemed to have skipped the line completely. They were massive, they were structured, they were thriving. They looked far too complex and far too old for the time they supposedly came from. One example stood out sharply. Astronomers identified a galaxy called Sears 1749, which appeared to exist only about 500 to 600 million years after the Big Bang. To put that in perspective, the Milky Way galaxy, our home, has taken over 13 billion years to reach its current size and structure. Yet Sears 1749 seemed to have gathered a mass comparable to the Milky Way within a tiny fraction of that time. It was as though someone had taken a shortcut in cosmic history, skipping over the slow stages of building and leaping straight to the finished product. According to the rules as scientists understand them, there simply had not been enough time for such a structure to form, and yet, there it was. What made matters even stranger was that these galaxies were not barely holding themselves together. They were not fragile or incomplete. They were alive with activity. Some were forming stars at astonishing rates, 10 to 20 times higher than the models had predicted. Others showed signs of calm, ordered rotation, with smooth galactic disks spinning gracefully, something that usually requires long stretches of time, large amounts of mass and stability to establish. Instead of chaos and disorder, there was elegance and maturity. The problem was not only about size, it was also about age, or rather, what age these galaxies implied. If galaxies were already well formed at such early times, then their stars must have begun forming even earlier, perhaps within the first 100 to 200 million years after the birth of the universe. That is an almost unimaginably short span of time. Cooling, collapsing gas clouds, the ignition of new stars, the shaping of galaxies, all of this would have needed to happen on a schedule far faster than the Big Bang theory allows. It was as though the universe, instead of slowly laying bricks, had built skyscrapers before the foundation was even dry. And then there was the issue of speed. These galaxies were not only big and old-looking, they were also building themselves with astonishing velocity. The rates at which stars were being born and mass was being added often went beyond what astronomers thought possible. In fact, many of them seem to be pushing past what is known as the Eddington limit, which is the theoretical maximum rate at which matter can fall into a structure before the radiation pressure pushes everything back out. According to this rule, you can only grow so fast before the very energy you release tears your structure apart. But these galaxies seem to be ignoring that limit, racing ahead as though the laws of physics were looser than we had believed. Taken together, these three traits, too big, too old, and too fast, form a triple contradiction. It is not a matter of explaining away one odd observation. To reconcile all of them at once requires bending the theory so far that it begins to lose its shape. Even if scientists try to adjust the details, the stress in the model does not vanish. Each new large galaxy discovered by Webb makes the tension worse, piling more weight onto the fragile bridge of the current understanding. Naturally, scientists began searching for ways to make sense of these puzzling results. One suggestion was that galaxies in the early universe might have been far more efficient at using their gas supplies than the galaxies we see today. Perhaps they simply burned through their fuel more quickly, forming stars with a kind of furious intensity that modern galaxies no longer sustain. But this answer only pushes the mystery backward. If efficiency explains it, why would such extraordinary efficiency appear so suddenly, in such large numbers, and across such vast stretches of the cosmos? Why did the models fail to predict it at all? Another idea was that dark matter, the invisible substance that makes up most of the mass in the universe, might have clumped together in the early cosmos to create deep gravitational wells. These wells could have pulled normal matter in more quickly, allowing galaxies to form faster than expected. But even this adjustment does not fully explain what Webb has revealed. It struggles with the sheer abundance of massive galaxies now visible, and it does not account for the chemical richness and organised structures observed within them. Some of these galaxies already show signs of metallicity, the presence of heavier elements that should only appear after many cycles of star birth and death. Yet there they were, gleaming with complexity. The questions become larger the more one looks. If our timeline for galaxy formation is so wrong, could it mean that the distances we measure, based mainly on redshift, need to be re-examined? Could time itself have flowed differently in the early universe than it does now? Or does the very model of cosmic expansion require revision? Perhaps even the laws of physics we take for granted today did not hold in the same way when the universe was young. These are not small matters. They ripple outward across the field of astrophysics like shock waves, touching every part of the science. The model that has long been considered solid, the so-called lambda cold dark matter model, or LCDM, has for decades explained the expansion of the universe, the faint glow of the cosmic microwave background, the large-scale clustering of galaxies, and much more. But James Webb is pressing against the edges of that confidence, forcing cosmologists to admit that the standard picture may no longer be enough. Some have gone so far as to call this moment a crisis in cosmology, a situation where either the theory must be seriously revised or radically reinterpreted. Meanwhile, James Webb itself continues to deliver images and data with breathtaking regularity. Every deep exposure reveals yet another galaxy that does not fit. Each new observation adds another layer of contradiction, another demand that the story be rewritten. The early universe, instead of looking like a messy construction site with half-finished structures, looks instead like a thriving cosmic city, an early metropolis bustling with activity long before it should have been possible. Whether this will topple the Big Bang Theory entirely is still an open question. Scientific paradigms do not collapse in a single night, no matter how surprising the evidence. History teaches us that theories bend, adapt, and shift before they ever break, but the rule is clear. When observation and theory collide, it is the theory that must change. The cosmos is what it is, whether our models can keep up with it or not. One of the most powerful and widely used ideas in the whole of astronomy is something called redshift. This single concept, simple in words but huge in meaning, is the main way that scientists measure how far away an object in space is, and by extension, how far back in time we are looking when we observe it. Redshift is not just a technical number on a graph, it is the very thing that allows us to take the scattered lights of galaxies across the heavens and arrange them into a timeline, almost like beads strung together on the long necklace of cosmic history. Without redshift, we would not know where to place these galaxies, how to tell if they are ancient or young, or how to weave them into the story of how the universe grew from a beginning into what we see now. But now, with the James Webb Space Telescope showing us details of the universe that no human eyes have ever seen before, something unsettling has crept into the picture. Some scientists are starting to ask questions that once seemed impossible, even forbidden. Could it be that we have misunderstood redshift? Could it be that this bedrock of modern cosmology, the very tool by which we plot the ages of galaxies and the distances of stars, is not telling us exactly what we thought? The mere suggestion shakes the foundations of astronomy, because everything from the Big Bang to the growth of galaxies has been painted using the brushstrokes of redshift. To understand the weight of this question, we must first take a careful, patient look at what redshift really is supposed to mean. When light leaves a distant object and begins its long journey across the expanding fabric of space, it does not remain unchanged. As space stretches, so too does the light that travels through it. A simple comparison is often given with sound. Imagine standing by the roadside as an ambulance drives away. The sound of its siren grows lower and lower in pitch as the vehicle recedes. That effect is called the Doppler shift. The same thing happens with light. When the source of light is moving away from us, its wavelength is stretched. Blue light, which has short, sharp wavelengths, becomes redder as those wavelengths lengthen. That is why the phenomenon is called redshift. In the world of cosmology, however, redshift is not just about motion. It is about the expansion of the entire universe. Space itself is stretching, carrying galaxies with it, and as it does so, the light coming from them also stretches. The higher the redshift, the farther away the object is, and importantly, the further back in time we're seeing it. Redshift is a kind of time machine. A galaxy with a redshift of 2 is being observed as it was when the universe was about 3 billion years old. A galaxy with a redshift of 10 is being seen as it existed when the universe was less than 500 million years old. The higher the redshift, the closer our gaze comes to the very dawn of everything, to the Big Bang itself. With this understanding, astronomers have built the entire history of the cosmos. They have traced the first stars, the first galaxies, the first black holes, and the changing rate of expansion of the universe. Redshift is not just a helpful measurement. It is the backbone of cosmic history, the ruler with which we measure the past. Without it, we would be lost, like sailors at sea with no compass and no stars. But the discoveries made with James Webb are deeply troubling. Galaxies seen at extreme redshifts, values of 10, 11, 12, and even beyond, are not behaving as expected. According to the timeline drawn from redshift, these galaxies should be tiny, fragile, and only beginning to assemble themselves into structures. Instead, they appear too large, too evolved, too organized, almost as if they had lived for far longer than the official timeline allows. They are like children who suddenly appear as fully grown adults skipping the years of youth. One possible explanation is that appearances are deceiving. Perhaps these galaxies only look older than they truly are. Maybe their brightness, their mass, or their internal structure tricks our instruments into overestimating their maturity. But another, far more radical possibility exists. Perhaps our interpretation of redshift itself is flawed. What if redshift is not telling us what we think it does? What if the stretching of light is not solely caused by the expansion of the universe? This question is not new. In fact, it reaches back to the earliest days of modern cosmology. In the early years of the 20th century, when Edwin Hubble first studied galaxies and discovered that their light was shifted toward the red, he proposed that they were moving away from us. This became the seed of the idea that the universe itself was expanding. Yet not everyone agreed. Some scientists came up with alternative explanations. One of the most famous was called the tired light theory. It suggested that photons, the tiny particles of light, gradually lose energy as they travel through space. Each interaction with particles or fields along the way would rob them of a little energy, stretching their wavelengths and making them redder. According to this view, redshift would not mean that galaxies were rushing away at high speeds. Instead, it would mean that light itself was simply getting tired after travelling unimaginable distances. For a while, this idea seemed reasonable, but over time it failed to match the precise observations astronomers gathered. The spectrum of the cosmic microwave background, the afterglow of the Big Bang itself, did not fit with tired light. Neither did the patterns of distant supernova explosions, which showed clear evidence of cosmic expansion. Gradually, the tired light idea faded, and the expanding universe model grew stronger. For almost a century, redshift was taken as the clear signal of expansion. Yet here we are again, with Webb's findings breathing new life into those old questions. If expansion alone cannot explain why young galaxies appear so mature at high redshifts, then perhaps there is another factor at work. Could redshift be influenced by things we do not yet understand? Could it be that photons change in ways more subtle than we ever imagined during their billions of years of travel? Some theoretical physicists suggest that space-time itself might not be smooth. Perhaps, especially in the early universe, space-time was rough, foamy, or filled with violent fluctuations at the quantum level. Light travelling through such a landscape might redshift in ways that differ from our current equations. Others speculate that photons could interact with dark matter or dark energy, the invisible components that make up most of the cosmos, in ways that subtly alter their frequency. Still others raise the possibility that at very small quantum scales, light behaves differently from what the standard model of physics predicts. If space is granular, if time itself is something that emerges rather than something that always existed, or if the speed of light has not been absolutely constant through cosmic history, then the foundation of redshift becomes shaky. Another unsettling realization is that much of our redshift calibration is built on models that we are now questioning. To estimate distances, we use redshift. But to confirm redshift, we rely on models of galaxy evolution, models that describe how galaxies should look and behave at different ages. This creates a dangerous circle. If the models are wrong, then the way we interpret redshift could also be wrong, and if the redshift interpretation is wrong, then the models collapse too. No one is suggesting that we throw out redshift entirely. It has proven remarkably consistent and predictive across countless observations, but the precision with which we equate a redshift number to an exact time and distance may need adjustment. Perhaps redshift still does indicate expansion, but not in a simple, linear way that fits all situations. Perhaps in the earliest epochs, something unknown distorted the relationship we have come to trust. Imagine building a map of history using a clock, only to discover that in the earliest hours of the clock's operation, the gears moved at a different pace than they do now. That is the kind of situation we may be facing with redshift. The clock of the cosmos may not have ticked at the same steady rhythm in its infancy. If this is true, then what we are seeing with Webb is not necessarily the failure of redshift, but the whisper of new physics. The debate is far from settled. Some scientists believe the mature galaxies at high redshift can still be explained within the old framework, by adjusting details of star formation, dust content, or black hole growth. Others are convinced that something deeper is at work. In the meantime, Webb continues to pour in data, revealing galaxies that challenge our understanding and forcing us to rethink assumptions that have stood for nearly 100 years. If redshift is not the simple ruler we thought it was, then the entire history of the universe may need to be rewritten. We may discover that galaxies formed faster, stars ignited earlier, or the fabric of space-time behaved differently than we imagined. Whatever the truth, it is clear that redshift, once seen as the most reliable tool in cosmology, has become the centre of one of the greatest scientific debates of our time. When the James Webb Space Telescope was first sent into space, one of its main goals was to finally capture a glimpse of the very first stars that ever formed in the universe. These stars, called Population 3 stars by astronomers, were expected to be unlike any others we know today. They were supposed to be extremely large, extremely hot, and made almost entirely of the two simplest ingredients in existence, hydrogen and helium. According to the standard story of the cosmos, these stars were the very first lamps that lit up the universe, the first torches to burn in the dark sea of space after the Big Bang. They were imagined to be born in a universe that was fresh, clean, and untouched by the heavier elements that would only come later. But when Webb looked deep into the early universe, the story that astronomers expected began to unravel. Instead of discovering the long-awaited pure and primordial stars, the telescope revealed something completely unexpected, stars that should not have been there so soon. These were stars that had already been altered by processes that, according to theory, should have taken hundreds of millions of years. Stars shining within ancient galaxies blaze not only with hydrogen and helium, but also with unmistakable signs of heavier elements, what astronomers call metals. In astronomy, the word metal does not mean iron alone, as it does in everyday speech. To astronomers, any element heavier than helium counts as a metal. That means carbon, oxygen, nitrogen, iron, and many others. But here's the astonishing part. These elements are not born in the beginning of the universe. They are made deep inside stars through the furnace of nuclear fusion. Only when stars die, often in spectacular explosions called supernovas, are these elements scattered across space, seeding the gas clouds that later give birth to new generations of stars. So, for Webb to detect metals in such early stars means that several generations of stars had already lived and died before these newly observed ones came into being. Yet, Webb was seeing these enriched stars only a few 100 million years after the supposed Big Bang. That is nowhere near enough time for several cycles of stellar birth, death, and recycling to take place. It is as if the universe had skipped steps, jumping ahead in its story before the chapters in between were written. According to the traditional Big Bang framework, things were supposed to unfold in a slower, more orderly way. First came the Big Bang itself, followed by a period called recombination, when the hot soup of protons and electrons cooled enough to form neutral atoms. After that, gravity gradually gathered clumps of gas together until the very first stars ignited. These population 3 stars, if they truly existed, were thought to live brief, violent lives, burning fiercely, then exploding as supernovas. Their explosions would scatter heavy elements across space, setting the stage for later stars, which would be richer in chemical variety. But this cycle of enrichment should have taken many hundreds of millions of years, not just a few. And yet Webb has uncovered something else entirely. In galaxies with names like GNZ1 and CR7109, astronomers are not seeing plain primitive stars. Instead, they see stars blazing with luminosity, stars that are not only massive but also chemically complex. That kind of complexity means that the universe had already gone through stages of star birth and star death, which, under current models, should not have been possible in such a short time frame. Some scientists, struggling to make sense of the findings, have suggested that maybe stars in the early universe simply formed much faster than we thought. Perhaps the conditions back then were so unusual, more crowded, denser, or influenced by violent collisions and shock waves, that stars could go through their lives more quickly. In this view, the first galaxies were like cosmic pressure cookers, speeding everything up. But even this idea seems stretched, because Webb is not just spotting a rare exception. It is not just 1 or 2 galaxies showing signs of metal-rich stars. It is finding this pattern over and over again across many different galaxies. That changes the whole picture. The early universe no longer looks like a blank canvas waiting for the first strokes of paint. Instead, it looks like a canvas already covered with vibrant colours and intricate details, as if someone had begun painting the masterpiece long before the opening chapter was supposed to begin. What makes the story even stranger is the sheer size of some of these stars. Webb's observations suggest that some of them may have been hundreds of times more massive than our own Sun. According to theory, such enormous stars should not even exist. Big stars are thought to be unstable, because the pressure from their own radiation would blow them apart or collapse them into black holes. But in the early galaxies Webb examined, these giant stars do not appear to be rare oddities. They seem to be common. How could this be? These massive, chemically enriched, blazing stars are not supposed to exist in such abundance, especially so soon after the beginning of the universe. For them to exist at all suggests that some unknown process must have been at work, something that gave the cosmos a head start. Even if we allow for rapid gravitational collapse and cooling, the window of time between the Big Bang and the birth of these stars seems impossibly short. This leads to unsettling questions. What if the universe did not start as a clean slate filled only with hydrogen and helium? What if, instead, the early universe was already chemically active, already busy forging complex elements, already building stars richer than theory allows? That would suggest either a very different beginning or a very different timeline than the Big Bang theory describes. Some alternative ideas, once pushed aside, have begun to receive a little more attention. Models like plasma cosmology or the steady-state theory propose that the universe did not start with a single explosive moment, but has always existed in some form, endlessly recycling matter and energy. In such views, stars that look early are not really early at all. They are simply part of a cycle that has been going on forever. These models fell out of favour long ago, but Webb's discoveries have rekindled a spark of interest in them. Of course, there is another possibility. Maybe our entire understanding of how stars form and evolve is missing key pieces. Perhaps the physics of the early universe allowed for faster nuclear fusion, shorter stellar lifespans, or exotic forms of stellar behaviour that we cannot yet explain. Perhaps dark matter, that invisible and mysterious substance we know so little about, played an unexpected role in sparking rapid chemical change. Or perhaps some unknown factor altogether was at work, shaping the early cosmos in ways we have not yet imagined. When most people think about black holes, they imagine them as the grim reapers of the universe, silent cosmic destroyers that swallow everything in their path. In the traditional picture painted by astronomy, black holes are supposed to be the final resting places of enormous stars that lived long, burned bright, and then collapsed under their own weight when their fuel was gone. In other cases, black holes are described as the monstrous hearts of galaxies, the super-heavy anchors that sit quietly in the middle, shaping everything around them with their invisible gravitational pull. Either way, these objects are supposed to be ancient, slow to form, and even slower to grow. The making of a black hole is not something that happens overnight, nor is it something that the universe was expected to do easily. Instead, it is thought to be one of the last chapters in the long and complicated story of stars and galaxies. To fashion a black hole, you need time. You need multiple generations of stars to live, die, and recycle their gas into new stars. You need great amounts of material to fall together, sometimes through violent galactic mergers and endless collisions. It is a brutal, grinding process, not a quick or elegant one. In fact, in the standard model of astronomy, black holes are the punctuation mark at the end of cosmic time. They are not supposed to be there at the very beginning. And yet, when the James Webb Space Telescope began to send back its breathtaking new images of the early universe, astronomers were confronted with something that seemed impossible. Black holes, enormous ones, supermassive ones with millions or even billions of times the mass of our Sun, were already there, lurking in the universe when it was still in its infancy. This discovery shook the foundations of astronomy. For a long time, scientists believed that supermassive black holes, those giants with masses millions or billions of times greater than our own Sun, only grew at the centres of galaxies after a very long history of star birth and galactic evolution. Our own Milky Way galaxy, for instance, holds such a monster at its centre. It is known as Sagittarius A star, and it is the steady gravitational anchor of our home galaxy. It took billions upon billions of years for that giant to form, grow, and settle into its role. But Webb's sharp eyes, looking deep into cosmic history, have revealed the unmistakable signs of these monsters, already fully active in galaxies that existed less than 700 million years after the Big Bang. To put this into perspective, the universe is thought to be about 13.5 billion years old. If these black holes existed only a few hundred million years after the Big Bang, that means they formed and grew in what amounts to the blink of a cosmic eye. And not just tiny black holes, some of these are hundreds of millions of times the mass of the Sun. By every standard model of astronomy, this should not be possible. The timelines simply do not work. Let us consider what the accepted story used to be. Imagine the very first stars of the universe, the so-called population 3 stars. These were enormous, hot, and short-lived stars made almost entirely of hydrogen and helium. When some of these collapsed, they could leave behind what astronomers call seed black holes, perhaps 100 times the mass of the Sun. That is already large compared to the remains of stars today. But to go from that to a black hole with hundreds of millions of solar masses is not a simple step. It requires the black hole to keep feeding, swallowing up gas and dust at a steady rate, colliding with other black holes when galaxies merge, and doing this for hundreds of millions or even billions of years. Even in the most optimistic models, it takes a very long time, and yet Webb sees them not just forming, but already fully grown, already dominating their host galaxies, already shining with the blinding light of matter spiralling into their hungry mouths. This is not just the early formation of black holes, this is early black hole domination. It suggests that from the very beginning of galactic history, black holes were not the quiet endpoints of stellar death, but rather the engines driving the growth of galaxies themselves. Some of the galaxies Webb has uncovered appear to be literally built around these giants. Instead of black holes being a byproduct of galaxy growth, as once thought, it now looks as if black holes may have been the central requirement for galaxies to form at all. It flips the traditional model upside down. It is as though we were reading a book and thought we knew the last chapter, only to discover that the story began with the ending already written. One particularly shocking example is a galaxy scientist called Sears, discovered by Webb's observations. This galaxy existed when the universe was only about 570 million years old, and yet at its centre there is a massive black hole that is not just sitting quietly, but is actively consuming gas. It is alive, so to speak, sending out great bursts of energy as it eats, changing its environment and shaping the galaxy around it. This is exactly the kind of behaviour astronomers expected to see in galaxies billions of years old, not in galaxies that had barely had time to form stars. How can this be explained? Some scientists propose that these black holes did not begin as the tiny 100 solar mass seeds left behind by the first stars. Instead, they might have formed directly from giant clouds of gas collapsing under their own weight, skipping the step of becoming stars entirely. This process, called direct collapse, could in theory produce seed black holes tens of thousands of times the mass of the Sun, which would give them a head start. If you begin with a bigger seed, you do not need as much time to grow into a supermassive black hole, but even this idea struggles to explain what Webb has revealed. For these black holes are not just big, they are already accreting matter, glowing as active galactic nuclei, while their host galaxies are still furiously forming stars. To grow so quickly, they would need not just a large seed, but also a perfect abundant supply of cold gas falling in smoothly without interruption. Yet our models of star and galaxy formation predict that such feeding should be messy, turbulent and self-limiting. And still, Webb finds them, monsters already in place, already active, already rewriting our cosmic history. The most unsettling part is that they are not rare. They are not occasional freak accidents of nature. These early supermassive black holes appear to be common. They are everywhere Webb looks. That means this is not a story about exceptions, but about a fundamental process. The universe, it seems, was designed to make black holes quickly and efficiently in its youth. If that is true, then everything we thought we knew about cosmic structure formation must be questioned. For decades, astronomers thought galaxies came first, and black holes were the consequence. But now it may be that black holes were there from the beginning, guiding galaxies into existence. This would mean they played a far greater role in shaping the early universe than anyone imagined. They may even have been central to the great transformation called rionization, when the first light sources turned the early universe from a fog of neutral hydrogen into the transparent cosmos we see today. The high-energy radiation pouring from these early black holes could have been a driving force in clearing away that fog, making the universe visible. This raises another possibility that some scientists find both thrilling and disturbing. What if black holes did not just appear from stars or gas clouds at all? What if they were present from the very beginning, formed out of the strange quantum fluctuations in the very first moments of the universe? These so-called primordial black holes would be objects born not from stellar death, but from the birth of time itself. In this view, galaxies did not make black holes. Black holes made galaxies. Around these first black holes, gas would gather, stars would form, and galaxies would take shape. Instead of being the universe's final chapter, black holes would be its opening act. It is a reversal that forces us to rethink nearly everything. For so long, astronomers believed in a slow, linear unfolding of cosmic history. Stars formed, then galaxies, and only later did black holes grow out of that process. Now the evidence suggests something different, something almost alarming in its implications. If supermassive black holes were already common less than 1 billion years after the Big Bang, then the universe must have leapt into complexity much faster than we thought. Perhaps it always had complexity built in from the beginning, waiting to be revealed. These revelations leave scientists with deep unease, but also with awe. For black holes are no longer just the silent reapers of stars. They are architects of galaxies, shapers of the cosmos, and maybe even the very seeds of creation itself. The James Webb Space Telescope, by peering back to those earliest days, has not just given us beautiful images, it has shown us a universe stranger, faster, and far more mysterious than we ever dared to imagine. Dark matter has long been imagined as the silent skeleton of the universe, the invisible framework upon which all visible things rest. For many decades, astronomers and physicists have spoken of it as though it were the unseen scaffolding that holds the grand cosmic architecture together. They say it is the strange and mysterious material that makes up more than 4/5 of all the matter in existence. yet it neither shines nor reflects nor interacts with the familiar forces that govern electricity and magnetism. You cannot see it, you cannot touch it, and yet its presence is said to be written across the heavens in the way galaxies spin, in the way stars are arranged, and in the way light itself bends and stretches on its journey across the depths of time and space. For most of modern cosmology, this has been the comfortable story. Dark matter is there, invisible but powerful, binding together the luminous stars and galaxies as a hidden hand. That, at least, is what we thought. But then came the James Webb Space Telescope, a machine so finely built, so carefully designed, that it has begun to take us closer to the very dawn of creation than humanity has ever looked before. This telescope has not only dazzled us with its pictures of ancient galaxies glowing from an age when the universe was young, but it has also unsettled the very foundations upon which our cosmic story has been built. As its golden mirror gathers the faint light of ancient stars, Webb does not only reveal beauty, it whispers trouble. It raises questions not only about how old or how large these primeval galaxies are, but about whether the very framework we thought was holding them together, this dark matter scaffolding, is behaving in the way our theories claim. The unease begins when scientists take the delicate data gathered by Webb and compare it with the predictions of the standard model of cosmology, the one known by its shorthand as lambda-cold dark matter, or simply LCDM. This model has been the trusted script of cosmologists for nearly half a century. According to it, in the early days of the cosmos, dark matter clumped together first. Though invisible, it was meant to be the stage setter, forming deep gravitational wells into which the ordinary matter, hydrogen, helium, and all the familiar atoms could fall. Once the stage was set, these clumps of matter would become the seeds of galaxies, stars, planets, and eventually life itself. In this drama, dark matter was never just a background extra. It was the lead actor, stepping onto the stage before any star had kindled, before any galaxy had taken shape. Without dark matter, according to the model, the story could not even begin. But Webb's sharp and ancient vision has brought back a troubling contradiction. The galaxies it sees, huge and well-structured, appear far earlier in time than LCDM allows. According to the model, if these galaxies had dark matter halos surrounding them, then those halos must have formed incredibly quickly, faster than the rules of the model permit. In other words, if dark matter was indeed doing the work it was supposed to do, it was working at an almost impossible speed. This is like watching a play in which the actors are already fully dressed and in place before the curtains even rise, when the script says they should still be rehearsing their first lines. The mystery deepens when scientists study not just the shapes and distances of these galaxies, but their very structure, the way they spin, the way their mass is distributed, the way their stars are arranged. The spectral fingerprints that reveal their weight and their rotation do not always match the expectations of galaxies dominated by dark matter. Some of them act as though they are being held together by far less of this invisible glue than our theories demand. It is as if the hidden hand has loosened its grip. This is not the first time that dark matter has revealed cracks in the neat story of cosmology. Even here in our nearby universe, astronomers have found galaxies that seem to defy the rules. One example is the strange galaxy catalogued as NGC 52DF2, which appeared to contain almost no dark matter at all. According to our theories, that should be impossible, because without dark matter, galaxies should fly apart, unable to hold themselves together. Yet, there it was, a ghostly collection of stars apparently held together with little or none of the mysterious substance. At the time, such findings were treated as oddities, local puzzles, strange exceptions that did not overturn the wider rule. But now Webb is showing us that in the earliest chapters of cosmic history, these strange exceptions may actually be the norm. The galaxies of the young universe are not behaving like galaxies ruled by dark matter should. Another troubling question comes from the very shape and order of the universe itself. According to the LCDM model, in the beginning, dark matter should have been almost smooth, spread nearly evenly with only tiny ripples of difference. Over time, these small variations would grow, slowly forming strands, filaments, and vast nodes, weaving together the cosmic web of galaxies and voids we see today. But Webb is finding something different. It sees galaxies in the early universe that are not only massive and mature, but are also closer together, more neatly lined, and sometimes surprisingly well-ordered compared to what theory allows. Without well-developed support from dark matter, this much order should not yet exist. The universe at that stage should still have been chaotic, unshaped, and raw. So where did the order come from? What sculpted these galaxies into place so quickly? The possibilities that arise from this puzzle are many, and none of them are comfortable. Perhaps dark matter is not as cold as LCDM claims. In the model, cold means that it moves slowly compared to the speed of light, allowing it to clump neatly and predictably. But if dark matter is warm, or if it interacts with itself in some hidden way, then maybe it could clump more quickly, or spread itself differently, creating galaxies faster than expected. Yet even these altered versions of dark matter create problems of their own. They often fail to match other lines of evidence, such as the delicate patterns in the cosmic microwave background radiation, the ancient afterglow of the Big Bang, or the way galaxy clusters behave today. In trying to fix one hole in the theory, they tear another. Another path of thought is even stranger. Perhaps the trouble lies not with dark matter, but with gravity itself. For decades, a handful of physicists have explored alternatives to Einstein's and Newton's laws, theories with names like modified Newtonian dynamics, or MOND, and tensor vector scalar theories known as TVES. These models attempt to explain the odd behaviours of galaxies not by invoking dark matter at all, but by suggesting that the force of gravity behaves differently on very large scales. Instead of unseen matter pulling galaxies together, perhaps gravity itself becomes stronger or weaker in ways we do not yet understand. These ideas have often been treated as fringe, because they struggle to explain all observations, especially the broad sweep of the cosmos. But Webb's findings may breathe new life into them, not as complete replacements, but as partners in some hybrid picture. A universe where both modified gravity and limited dark matter play their parts together. And then there is the most radical thought of all. Perhaps dark matter, at least in the form we have imagined for almost 50 years, does not exist. Perhaps our equations of gravity and mass and energy are incomplete. Perhaps we have been working with only part of the script. The persistent mismatch between predictions and what Webb reveals might be pointing us toward a layer of physics we have not yet discovered, a hidden rulebook that reshapes the very way we understand the universe. This is not a small problem, for dark matter is not just a filler in our equations, it is the cornerstone upon which modern astronomy, astrophysics, and even particle physics have been built. It explains why galaxies form, how they cluster, how the great structures of the universe have risen from chaos. If dark matter fails, it is not one domino falling, it is the entire chain. And yet, Webb does not directly see dark matter. It cannot. No telescope can. What it does is push the boundaries of what can be seen in time and clarity. It shows us galaxies so early and so sharply that we're forced to ask, if dark matter truly existed in the way we imagine, would the universe look like this? And so far, the answer is becoming more uncertain. The neat story no longer fits the unfolding evidence. The great irony is that dark matter was meant to be the solution to earlier problems. It was invented to explain why galaxies spin the way they do, why clusters of galaxies hold together, why the large-scale universe has its structure. Without it, the numbers never added up. But now, the same solution seems to be breeding fresh puzzles. The invisible hand is either too quick or too weak, too strange or too absent. In every direction Webb peers, the story of dark matter grows more complex, more slippery. Perhaps, in the end, the universe is telling us that its secrets are not so easily bound by a single hidden substance. Perhaps there is a deeper symmetry, a hidden layer of law and order beneath both matter and energy, one that we have only begun to glimpse in the faint light of galaxies born when the cosmos was young. Maybe in the future, new theories will rise that do not simply patch holes in the old model, but rewrite the very foundations of cosmology. For now, though, we live in the shadow of doubt, watching as the elegant edifice of LCDM bends under the weight of Webb's revelations. And yet, this uncertainty is not despair. It is the thrill of discovery. For every time the universe defies our expectations, it invites us to imagine more deeply, to look more carefully, to stretch our understanding further than before. Dark matter may be fading as the single unquestioned answer, but in its place may rise something even more astonishing. A new chapter in the story of existence itself, written in starlight and shadow, in the unseen and the seen, in the questions that now burn brighter than the answers we once thought secure. For many decades, the idea of cosmic inflation has stood as one of the most daring and powerful explanations of how our universe came to look the way it does. It was not part of the earliest version of the Big Bang theory, the version that had been taking shape since the middle of the 20th century. Instead, it came later, in the early years of the 1980s, when scientists realized that the Big Bang theory on its own had some serious holes in it, gaps that needed filling. Cosmic inflation was a bold answer to these gaps. It was not shy or modest in what it claimed. In fact, it proposed something extraordinary, that in the very first instant of cosmic history, only a tiny fraction of a second after the Big Bang, the universe expanded at a speed faster than light itself. For a moment so brief that no clock could ever truly measure it, space itself stretched and grew at an exponential rate, meaning it doubled and doubled again, over and over, so rapidly that it became unimaginably vast in less than a heartbeat of cosmic time. The result of this sudden, breathless expansion was that the universe was smoothed out, flattened, and made uniform in ways that, without inflation, would seem almost impossible. A small curved patch of space, if stretched enough, becomes so wide and even that any sense of curvature is flattened out like wrinkles ironed from a sheet. Inflation proposed that this is what happened to the cosmos. By inflating, it became geometrically flat. By inflating, it spread regions that were once close together so far apart that today they look like they could never have touched. By inflating, it explained why the universe, when we look at it with our most sensitive telescopes, looks remarkably even and similar no matter which direction we point our eyes. This solved some of the biggest puzzles that had troubled cosmologists. One of them was the horizon problem. If we look in one direction, at the edge of the observable universe, and then in the opposite direction, at the other edge, we see that the light and heat from those regions look almost exactly the same. The temperatures are almost identical. The distribution of matter is strikingly similar. But the problem is that these two regions are so far apart that light could not possibly have travelled between them, not even at the maximum speed of light, within the age of the universe. They should never have been able to talk to each other, never able to share heat or information. Yet they look coordinated, as if they were once in close contact. Inflation offered a clever solution. Those regions were once together, able to exchange light and heat, before inflation suddenly blew them apart faster than light could chase them. That meant their similar appearance was not a coincidence, but a memory of their earlier connection. Another puzzle was the flatness problem. The equations of general relativity tell us that the universe could easily have been curved like a saddle or a sphere. A flat universe, the kind we see, is actually the most unlikely state of all. It requires the starting conditions to be tuned with exquisite precision, so precise that without a deeper explanation, it feels almost like a cosmic miracle. Inflation came to the rescue once again. A small curved space, if expanded to a gigantic scale, looks flatter and flatter until the curvature becomes invisible. Just as the Earth's surface looks flat to someone standing in a field, even though we know it is round, the universe after inflation would look flat to us because the curvature was stretched beyond recognition. So inflation seemed neat. It seemed clever. It tied together loose ends with mathematical beauty. But in its early years, there was one major issue. It did not actually produce testable predictions. It was a brilliant idea, but it was speculative, a theory built to fix problems rather than to forecast outcomes. For many years, this left inflation on shaky ground. It was admired for its ingenuity, but distrusted for its lack of hard evidence. Later, refinements gave the theory more rigour. Scientists showed that inflation could leave behind certain fingerprints in the oldest light of the universe, the cosmic microwave background radiation. This faint afterglow of the Big Bang carries tiny ripples, fluctuations that inflation could explain. Inflation predicted that these ripples would follow a particular pattern, with some sizes of fluctuation more common than others. When satellites like COBE, WMAP, and later Planck measured the cosmic microwave background in exquisite detail, the results lined up almost perfectly with inflation's predictions. Suddenly, inflation was no longer just a bold guess. It was the new standard. It became doctrine in cosmology, woven into the story of the Big Bang as if it had always been there. But even while it gained mainstream acceptance, inflation always carried an air of improvisation, of creativity stretched to its limits. It was, at heart, a patch, a fix layered on top of another fix. It worked brilliantly on paper, but But it was not born from first principles. It was invented to cover gaps. That gave it a slightly uneasy place in the grand structure of physics. Now, in the 21st century, a new generation of telescopes is forcing us to reconsider inflation once again. The James Webb Space Telescope, launched in the early years of the 2020s, is peering deeper into the past than we have ever done before. Webb cannot see inflation directly. That event would have occurred about 1/10,000th of a trillionth of a trillionth of a trillionth of a second after the Big Bang, so early that even light itself had not yet emerged. But Webb can see the consequences of inflation, the structures and shapes that resulted from it. What Webb is finding is unsettling. The galaxies that it detects in the deep past do not look like the rough, chaotic sketches that theory predicted. They do not appear as clumps of matter still struggling to organise themselves. Instead, they look too neat, too massive, and in some cases too mature for their age. They appear not as infants but as young adults, with large masses and orderly spins, as if they bypassed the messy childhood of galactic evolution. This is a problem for inflation. Inflation was designed to take a smooth, almost featureless early universe and add small irregularities to it, tiny quantum fluctuations that would grow slowly into galaxies, stars, and clusters. Those irregularities were supposed to be the seeds of structure. But if galaxies appear almost instantly in complex ordered states, then what role did those seeds really play? Did they even have time to grow at all? The paradox begins to flip on itself. Instead of too little irregularity, we may be seeing too much structure too soon. Inflation was supposed to sprinkle just the right amount of randomness into a smooth universe. But Webb's galaxies suggest a cosmos that leaped straight from smoothness into complexity, without the slow build-up inflation predicts. That raises troubling questions. Did inflation happen in a way very different from what we imagined? Or is it possible that inflation did not happen at all? Inflation predicts a very specific pattern of fluctuations, with certain sizes of structure more likely to appear. Yet the cosmic web, even at the earliest times we can see, looks puzzlingly uniform. The observed structures do not line up as neatly with the predicted spectrum. If this pattern continues as Webb gathers more data, we could be facing a deep inconsistency between the universe we see and the inflationary universe we imagined. And beyond these scientific puzzles, inflation carries philosophical baggage. The mathematics of inflation often lead naturally to the idea of eternal inflation, where the process never ends but keeps happening in distant regions, creating an infinite number of universes. In this picture, our cosmos is just one bubble among countless others in a vast multiverse. But here lies the problem. By definition, these other universes can never be observed. They are forever outside our reach. That means the theory is almost impossible to disprove, and a scientific theory that cannot be disproven begins to look uncomfortably like philosophy. Some physicists consider that a dangerous direction, because science is supposed to be testable, falsifiable, and grounded in evidence. So Webb's discoveries return us to a very old and very basic question. Did the universe really need that breathless moment of unthinkable expansion to become what it is? Or were we using inflation as a convenient cover, a mathematical plaster to hide cracks in a model that never fully held together? Some scientists are now daring to revisit older and more radical alternatives. There are models in which the universe did not begin with a singularity at all, but with the collapse of a previous universe that rebounded into our own. These bouncing or cyclic cosmologies imagine time as an endless cycle of birth, death, and rebirth, with no single beginning. Other researchers are exploring frameworks of quantum gravity, where space and time themselves may not be fundamental, but instead emerge from deeper laws. In such models, the very concept of inflation might not even be necessary. The debate is once again wide open. Inflation, once the clever fix that became the accepted truth, is now under pressure. The more we look at Webb, the more we may be forced to admit that the story we have been telling about the universe's first instant may not be the right one. And if inflation falls, we may need to build an entirely new narrative, one bold enough to replace it, just as inflation once replaced the gaps of the original Big Bang. When most people imagine the early universe, they picture a place of wild chaos, a storm of furious energy, particles flying everywhere, and a kind of turbulence that is almost impossible to put into words. It was not a calm or gentle birth. The beginning of everything was a furnace hotter than anything we can create on Earth, a cosmic explosion of unimaginable scale. From this fiery start, the universe was supposed to slowly cool, settle, and gradually change into a place where gas, stars, and galaxies could take shape. Out of the chaos, denser regions were supposed to appear, little by little, and these dense pockets of matter would, over time, grow into the great families of stars that we now call galaxies, and into even larger gatherings of galaxies that we know as galaxy groups and clusters. The idea of cosmic inflation was later added to the story of the Big Bang to explain some of the puzzling details of this beginning. Inflation is the notion that just after the universe was born, space itself expanded at an astonishing speed, faster than even the speed of light, though this does not break the rules of physics because it was space itself stretching, not matter moving through space. This inflationary burst smoothed out the universe on large scales. Instead of being wildly uneven, the universe became mostly the same everywhere, with only the tiniest flaws and irregularities scattered across it. These flaws, or tiny imperfections, were thought to come from quantum ripples, the smallest possible fluctuations in energy at the quantum level, which were suddenly stretched across cosmic distances by inflation. As strange as this sounds, those tiny little ripples were crucial. Without them, nothing interesting would ever have happened. A universe that was perfectly smooth would have stayed smooth forever, like an endless ocean of still water without a single ripple or wave. For galaxies to form, there needed to be tiny gravitational bumps, slight clumps of matter that could pull more matter toward them. Over billions of years, these small clumps would snowball into bigger ones, gathering gas, forming stars, and eventually building galaxies, planets, and life itself. Without the flaws created by those early ripples, there would be no us to wonder about the beginning. We even have a picture of these imperfections in the form of the cosmic microwave background, often called the CMB. This faint glow is the leftover heat from the early universe, the light released when the cosmos cooled enough to let photons or particles of light travel freely. It is like the baby picture of the universe, taken when it was only about 380,000 years old. If you look closely at the CMB, it is not perfectly even. It has faint temperature fluctuations, tiny differences of only a fraction of a degree, but those differences are the fingerprints of the first seeds of structure. They are the scars of those quantum ripples that inflation stretched into the vast canvas of the universe. Scientists have studied these fluctuations for decades and have built entire models of cosmology around them. Yet now, a new eye on the cosmos is shaking this story. The James Webb Space Telescope, humanity's most powerful observatory, has begun to peer into the early universe with clarity far beyond what the Hubble Space Telescope could manage. What it sees is not exactly what we expected. Instead of finding a universe still clumsy and messy, a cosmos that was just starting to put its building blocks together, Webb sees something that feels far too calm, far too orderly, and almost unnervingly advanced for its age. The pictures reveal galaxies that appear far earlier than they should, galaxies that already look well formed, spinning in neat arrangements, coming together in clusters in a surprisingly consistent way. The universe is not supposed to look like this when it was only a few 100 million years old. It is as if the cosmos skipped the awkward teenage years and leapt straight into adulthood. Instead of clumps and irregular shapes that slowly merge, Webb shows galaxies appearing in tidy forms, with ordered spins and balanced structures. It is not that galaxies are spread out evenly everywhere, far from it. They are still scattered, but the pattern of their appearance, the way they form, and the rate at which they're growing looks far too smooth, too clean, and too advanced. This is unsettling, because according to the inflationary model and decades of cosmological simulations, the early universe should not be this neat. Inflation predicted small fluctuations that would lead to clumpy, uneven distributions of matter. These clumps were supposed to collapse under their own gravity and gradually evolve into complex shapes, the tangled web of filaments and voids we see today. But Webb seems to be catching the universe in the act of skipping the chaos. In its images, some fields of view show galaxies that are remarkably uniform in both size and shape. They look too organized, too early. Structures that should have taken billions of years to emerge seem to already be standing tall just a few 100 million years after the Big Bang. This raises a troubling question. Did inflation work too well? Some scientists have wondered for years if inflation, while solving many early problems, might have created another one. It smoothed the universe so effectively that perhaps it left too little room for the natural messiness of structure formation. If the universe was ironed out so quickly and so thoroughly, where did the bumps and clumps come from that were supposed to grow into galaxies? The galaxies Webb is seeing should not exist in such numbers and such shapes if inflation smoothed everything out too much. Yet they do exist, and we are forced to confront that. There are several possible explanations being discussed, but none are fully satisfying. One idea is that our understanding of how gas and dark matter collapsed under gravity in the early days might be incomplete. Maybe matter gathered together faster than we thought possible. Perhaps dark matter behaved differently, or perhaps gas cooled more efficiently, letting stars form earlier. But even in these scenarios there are limits. Gravitational collapse takes time, and star formation requires certain conditions. You can imagine turning the dial to make star formation more efficient, or imagining dark matter that is colder and clumpier than our standard models suggest, but it still does not fully explain the sheer scale and order of what Webb is finding. Another possibility is that the cosmological simulations we've been running for decades are oversimplified. These are computer models that try to follow the laws of physics to see how the universe should evolve, from the earliest fluctuations to the complex web of galaxies we see today. But simulations are only as good as the assumptions and equations we feed into them. If we have been missing some ingredient, then perhaps the universe evolves differently than our models say. If this is true, it is not just a small correction. It would call into question decades of predictions, including the shape of the universe, the timing of galaxy formation, and even the role of dark matter. Some have suggested that maybe we're being tricked by an illusion. Perhaps we're only seeing a handful of galaxies that, for reasons we do not yet understand, formed much earlier than their neighbours. Maybe they are rare exceptions, flukes of physics, while the rest of the universe was still catching up. But as Webb continues its surveys, this explanation grows weaker. The anomalies are not rare. They are common. They are everywhere Webb looks. The early universe seems filled with galaxies that are too grown up for their age. There is also the broader puzzle of why the large-scale structure of the universe is so balanced in the first place. On cosmic scales, the growth of galaxies, the spread of matter, and even the curvature of space itself seem to line up with astonishing precision. It is as if the universe was tuned in advance for the formation of galaxies. Inflation was supposed to explain this by smoothing everything out, but Webb's results suggest an even higher level of precision than inflation alone would predict. The accuracy is eerie, almost as if the cosmos knew exactly what it was doing. This forces us to ask daring questions. What if the universe was never a chaotic mess that slowly grew into order? What if, instead, the universe began with some kind of encoded complexity, a blueprint already in place? That would mean reimagining the very beginning of everything, not as a singular explosive chaos that stumbled its way into structure, but as something closer to a ready-made system. A cosmos that did not have to struggle to build complexity, but began with complexity already written into its foundations. Such a thought shakes the very core of cosmology. It would mean the initial conditions of the universe were far stranger and more structured than we ever imagined, or that perhaps the idea of a singular beginning, the Big Bang as we understand it, is not the full story. The James Webb Space Telescope was built to give us clarity, but sometimes clarity brings confusion. By looking further into the past than ever before, it may be showing us that our most trusted models of cosmology are incomplete. The galaxies Webb sees are not supposed to be there, yet they are. The early universe looks too smooth, too calm, too organised, and too advanced. For a cosmos born in fire and chaos, this is a mystery that demands answers. It was bound to happen sooner or later. With every great discovery in the history of science, there always comes a moment when something appears that does not fit, something that seems to shatter the carefully built order of theories and models. When the James Webb Space Telescope began to send back its very first deep-field pictures of the universe, astronomers expected excitement, beauty, and clarity. They were prepared for breathtaking sights of distant galaxies, for new wonders hidden in the depths of space. What they were not prepared for, however, was the shock of seeing things that by all the rules of normal physics should not exist. These were not small errors or poetic exaggerations. They were plain, direct, and deeply unsettling contradictions. The galaxies that Webb revealed were not simply unusual. According to the laws that scientists have trusted for decades, they were impossible. For a long time, astronomers had carried certain expectations about what the early universe would look like. The framework of the Big Bang theory, refined over the years and reinforced with countless simulations, had told us a very clear story. After the first great explosion that marked the birth of the universe, matter needed time to settle, to cool, and to begin forming into the earlier structures. Gas clouds would gather and slowly collapse under gravity. Stars would ignite in clusters after hundreds of millions of years. Galaxies, the great cities of stars, would take even longer, slowly building up their complexity over time. When astronomers looked back to those very first few 100 million years after the Big Bang, they expected to see primitive objects, small, chaotic, gas-rich clumps, half-formed, messy, and unstable. They expected to see stars just beginning to shine, dust clouds swirling in confusion, and the first sketches of order only just appearing. What they did not expect was maturity, and yet, when Webb aimed its powerful golden mirrors toward the farthest corners of the cosmos, it showed something that left even the most cautious scientists astonished. Instead of small fragments of half-born galaxies, there appeared bright, massive, fully formed galaxies glowing at astonishingly high redshifts, values of 10, 12, and beyond. These redshifts told astronomers something extraordinary. These galaxies existed when the universe was only a few 100 million years old, less than 2% of its current age. The galaxies were not faint suggestions of future order. They were robust, brilliant, and undeniably real. They were too big, too bright, too well organized, and, most disturbing of all, far too numerous to fit into the neat and carefully drawn timeline of the Big Bang. The problem was not merely that these galaxies had been seen earlier than expected. The deeper issue was that they had already achieved so much by that impossibly early time. Some of them contained as many stars as our own Milky Way, a galaxy that took billions of years to assemble. Others displayed the kind of order that only comes with age: large disks, stable patterns of rotation, and rich chemical compositions suggesting that several generations of stars had already lived and died within them. These galaxies did not resemble babies. They resembled adults walking confidently in a universe that was still in its infancy. It was as if someone had discovered entire cities, complete with skyscrapers and highways, in a world where only mud huts were supposed to exist. Among the most striking examples is a galaxy that Webb captured, catalogued under the name Sears 93,316. This galaxy has a redshift of about 16.7, meaning that we are seeing it as it appeared only about 240 million years after the Big Bang. To grasp how shocking that is, one must remember that, according to standard models, this is a time when the universe was still in its earliest recovery from the violent heat of its birth. Gas clouds should barely have begun cooling. The very first stars, known as population 3 stars, were just expected to be flickering into existence. There should not have been enough time to form even a modest galaxy, let alone one as organised and luminous as Sears 93,316. Yet Webb's instruments showed it clearly, a galaxy not struggling to be born but already standing in maturity. Why do scientists call such galaxies impossible? It is not simply because they appeared too soon. The real impossibility lies in the way physics describes the processes that create stars and galaxies. To form stars, gas clouds must first collapse under gravity, and this takes time. The gas must cool, compress, and overcome instabilities before nuclear fusion can begin. To build galaxies, countless stars must gather and organize, their gravity weaving them into a structure. To enrich those galaxies with heavier elements, generations of stars must be born, live out their lives and die in supernovae, scattering metals into space for new stars to form. These processes are not shortcuts. They are bound by the limits of physics. They require time, hundreds of millions and even billions of years. And yet somehow these galaxies managed to do all of that within only a sliver of cosmic history, within the first 2% of the universe's existence. It was as if the natural clock of cosmic evolution had run at 10 times or 100 times its normal speed. At first, many scientists were cautious. Perhaps these objects were not what they seemed. Perhaps the redshifts had been miscalculated. After all, redshift is often measured from faint, distant light, and it is easy for photometric confusion or contamination by nearby objects to create mistakes. Some astronomers suggested that these galaxies might not be so far away after all. They could simply be closer, younger galaxies masquerading as ancient ones. But then the spectroscopic data began to arrive. Webb's instruments are precise enough to measure light at the level of individual spectral lines, and these confirmed beyond doubt that the redshifts were real. These galaxies truly were as far away and as early in time as they appeared. The uncomfortable truth could no longer be ignored. The impossible galaxies were real. This discovery has set off waves of debate and concern within the astrophysics community. For decades, scientists have relied on a model of the universe called lambda-cold dark matter, or LCDM. This model has been our cosmic compass. It tells us when galaxies should form, how fast they should grow, and what they should look like at different ages. Entire generations of simulations have been built upon it. Now, Webb has pulled back the curtain on the cosmic stage and shown us something very different. A universe that was already bustling with fully developed galaxies long before the script said they should arrive. It is not simply that new actors appeared earlier than expected. It is as though the entire play had skipped its opening acts and jumped straight to a middle scene. Faced with this puzzle, theorists have begun searching for explanations. Some propose that early galaxies must have been extraordinarily efficient at turning gas into stars, far more efficient than the galaxies we see today. Perhaps conditions in the young universe allowed matter to collapse and ignite much faster than expected. Others suggest that hidden forms of matter, perhaps ultra-dense halos of dark matter, accelerated the collapse and sped up the process of galaxy formation. These are intriguing ideas, but they raise difficult new questions. If early galaxies were truly so efficient at star formation, why do we not see the same behaviour later in the universe's history? If dark matter halos collapsed so quickly, what does that say about the nature of dark matter itself? A mystery that already challenges scientists at every turn. Every patch to the model seems to create more holes. And perhaps the deepest question of all is this: why did our models fail to predict any of this? For years, cosmological simulations have given us confidence that we understood the timeline of the universe. The Big Bang framework, combined with dark matter and dark energy, painted a picture that matched observation after observation. But now, Webb has revealed a universe that is far more advanced, far earlier than we ever imagined. It suggests that our cosmic story may have been written with the wrong clock, that we may have misunderstood the pace at which complexity arises. If galaxies could grow up so quickly, what else have we misunderstood about the early universe? Was it not a slow and steady climb from simplicity to complexity, but rather a sudden leap into structure and order? Today, the mystery of the impossible early galaxies has become one of the hottest topics in modern astronomy. It has unsettled the foundations of cosmic theory and left scientists scrambling for answers. It is not just a matter of adjusting a few numbers in a model. It is a challenge to the very timeline of the cosmos. It forces us to ask whether the framework that has guided us for so long is fundamentally incomplete. Do we need to rewrite the story of cosmic dawn from the ground up? Do we need entirely new physics, new ideas about dark matter, or even new understandings of the Big Bang itself? The sense of urgency is palpable. The galaxies Webb has revealed are not faint, isolated anomalies. They are numerous, clear and undeniable. They stand as a chorus echoing across space and time, declaring that something in our understanding is broken. They are reminders that the universe is not obliged to match our expectations, that nature often has surprises waiting just beyond the reach of our instruments. With every observation, Webb deepens the puzzle, giving us more examples of galaxies that should not exist but do. These galaxies shine not just as points of light in the sky, but as symbols of the unknown, daring us to rethink everything we thought we knew about the beginning of the universe. And so we find ourselves at a crossroads. Either we must stretch and bend our current models beyond recognition, or we must accept that it is time for a new one. The impossible galaxies are not just distant curiosities. They are cracks in the foundation of cosmic theory, cracks that could lead to a profound reshaping of our view of time, matter, and the very nature of the universe itself. The story of the early universe has always been told as a tale of slow beginnings. In the traditional view, the cosmos did not suddenly burst into its present richness and beauty. Instead, everything was meant to unfold step by step, gradually building up complexity as the ages passed. According to this picture, galaxies did not simply switch on like lamps in the night sky. They were thought to start as nothing more than hazy clouds of hydrogen and helium gas, floating almost invisibly in the emptiness. Gravity would slowly pull these gases together, squeezing them into clumps that grew denser over time. Within those clumps, the first stars would ignite, burning with brilliant but short lives. When those first stars died, they would scatter heavier elements into space, adding richness to the raw materials of creation. Through many cycles of birth and death, through endless gathering and reshaping, these clouds would eventually transform into the elegant and massive galaxies that we see today. For a long time, this story of slow transformation seemed convincing. Astronomers believed that the universe was a patient artist, sketching with faint lines before painting with bold colours. Billions upon billions of years were required for this masterpiece to take shape, turning simple beginnings into intricate cosmic cities of stars. But now, with the James Webb Space Telescope gazing deeper into time and space than any instrument before it, the story looks less certain. What Webb has revealed is something profoundly unsettling, something that does not fit easily into the old narrative. Instead of finding galaxies in their infancy, struggling to form or stumbling through their early stages, Webb is uncovering galaxies that appear fully grown. They are not rough sketches waiting to be finished. They are complete, complex, and already mature, appearing only a few 100 million years after the event we call the Big Bang. When scientists look at the telescope's deep field images, they see entire collections of galaxies shining brightly, with structures and behaviours that look almost like the galaxies we see in our own time. This is shocking because, according to the standard picture, the universe was not supposed to work this way. After the Big Bang, there was a long period known as the Cosmic Dark Ages. This period stretched from the release of the cosmic microwave background, essentially the afterglow of the Big Bang, until the first stars began to shine. That time should have lasted roughly 200 to 300 million years. During it, the universe was cooling down, the hot plasma thinning into neutral atoms, while gravity only slowly began to tug matter into the first small clumps. Out of those clumps, the earliest stars were supposed to ignite, messy and unstable, small and metal-poor. The galaxies that grew from them were expected to look clumsy, chaotic, and unrefined. Yet the Webb telescope is showing something entirely different. It is not finding scattered fragments of gas trying to light their first stars. Instead, it sees well-formed galaxies with spiral arms, bulges, and chemical fingerprints that suggest multiple generations of stars have already lived and died. Some of these galaxies even show signs of star formation activity that rivals what we see in modern galaxies today. In other words, instead of watching the universe's awkward teenage years, we are peeking directly into its adulthood. The puzzle deepens when scientists measure the mass of stars within these young galaxies. In several cases, the stellar mass is comparable to that of the Milky Way itself. That is almost unthinkable, because it means that those galaxies had to produce stars at breakneck speed, converting enormous amounts of gas into suns at an efficiency no current model of physics can explain. Even the most extreme scenarios, like sudden bursts of star formation triggered by violent collisions, cannot explain how galaxies of such size and complexity appeared so soon after the supposed beginning. If this is true, it implies that our cosmic timeline is wrong, not just by a little, but by staggering amounts. Instead of galaxies taking billions of years to grow from scattered gas clouds, it seems they may have taken only a few 100 million years. That is like expecting a newborn child to be running, speaking and solving puzzles almost immediately after birth. This revelation raises troubling questions. What does it mean if the universe did not slowly evolve into complexity, but instead began already complex? The strength of the Big Bang model has always been its ability to tell a coherent story, how the hot and simple beginning slowly cooled and diversified into the immense variety of structures we see today. But if complexity was present almost from the start, then the story changes dramatically. Instead of a universe gently unfolding, we may be looking at one that appeared ready-made, with galaxies already organized, structured, and functioning. That does not necessarily mean the universe was created by design or magic, though such ideas naturally creep into people's minds when science stumbles upon mysteries. More likely, it means that we do not yet understand the rules that governed those earliest times. Perhaps the physics of the young universe followed principles that no longer apply today. Maybe matter interacted differently, or gravity behaved in unusual ways, allowing structures to form at a speed we would now call impossible. There is another possibility that unsettles astronomers. What if time itself behaved differently in the beginning? If time did not flow in the same way it does now, our measurements of age and distance could be misleading. The main tool astronomers use to measure cosmic age is redshift, the stretching of light as the universe expands. But if redshift is not as reliable as we believe, or if distances are not being calculated correctly, then perhaps these galaxies are not as old as they appear. That would buy us some extra time, but not nearly enough. Even the most generous corrections could not transform a few 100 million years into the billions of years required by traditional models of galaxy evolution. What makes the puzzle even stranger is the consistency of what Webb is finding. If only 1 or 2 galaxies had broken the rules, scientists might have explained them as rare oddities. But Webb's images show entire populations of mature galaxies appearing far earlier than expected. This is not an exception. It is a pattern, almost as if the universe, from its earliest moments, was prepared to display complexity on a grand scale. Some cosmologists have begun using vivid imagery to describe the situation. They say the early universe looks like a stage play. When the curtain rises and the lights come on, the actors are not rehearsing. They are already dressed in costume, speaking their lines with confidence and performing in a well-prepared production. The stage is not bare or messy. It is fully decorated, organised, and ready for an audience. That image runs directly against the gradual step-by-step model of growth that has dominated astronomy for decades. If the universe truly appeared ready-made, it means that whatever forces shaped it were faster, more efficient, and more organised than anything our current theories allow. It challenges the very foundation of the story we have been telling for generations. The Big Bang model may still describe a beginning, but the way that beginning unfolded could be far stranger than we ever imagined. The Webb telescope's discoveries are not the final word, of course. Each new piece of data raises new questions, and scientists are still working furiously to make sense of what they are seeing. Yet even in this early stage of analysis, the message is clear. The universe is not as simple, not as gradual, and not as predictable as we once thought. The deep field images show us not a childlike cosmos learning to walk, but an adult universe striding confidently from the start. For many decades, scientists, dreamers, and explorers of the skies have been waiting for the day when humanity could finally see what they called the cosmic dawn. This is not just a poetic phrase. It describes one of the most important moments in the history of everything that exists. It is the instant when the very first stars were born, when their light ended the long dark ages and began to illuminate the young universe. Before that time, the cosmos had been filled with darkness and silence, a vast ocean of potential without any true brilliance. The coming of the first stars was supposed to be the event that transformed the universe from emptiness into form, from stillness into motion, from shadow into light. The universe at that moment was thought to be a quiet and uncertain place. Astronomers imagined that small, scattered stars would slowly flicker into existence, separated by huge distances and shining against a background of neutral hydrogen gas. These first points of light, like tiny sparks on a dark canvas, were meant to slowly gather together, building the very first galaxies. It was supposed to be a hesitant, delicate beginning, a soft and patient rise from nothingness toward complexity. Scientists thought that if we could witness that moment, we would see the gentle unfolding of order, the very first chapter of the story of form and structure. But when the James Webb Space Telescope finally began to return its early images and data, something deeply unsettling appeared. The story was not as quiet or as slow as expected. Instead, a haunting possibility began to emerge. What if the moment we have been calling the universe's dawn was not really a dawn at all? What if what we thought was the first soft light of sunrise was in fact the brightness of midday? What if creation was already far ahead of where we imagined? Not a hesitant beginning, but a bustling, luminous stage that looked much more like the middle of a story than the start. The very phrase cosmic dawn suggests a beginning. It brings to mind the idea of the first glow of sunlight, the hesitant start of a new day, the slow and steady rise of brightness that leads to the fullness of noon. In the same way, scientists thought the first galaxies would be weak, small and simple, just starting to grow, hardly more than flickers in the void. But the galaxies Webb has seen at astonishingly high redshifts of 10, 12, and even as high as 16, do not fit that description. Instead of being faint or uncertain, they are blazing with brilliance. They are structured, they are dynamic, they are creating stars at a pace that rivals, and in some cases exceeds, the star-making activity of modern galaxies billions of years later. Some of these ancient galaxies are shining brighter than galaxies that came into being much later in cosmic history. This is not a flicker. This is not a hesitant spark. This is a full blaze. This discovery is not just surprising, it is almost terrifying, because it challenges the very foundations of how we thought the universe worked. The long-standing belief was that the universe started simple and slow, gradually becoming more complex over billions of years as stars and galaxies formed, lived, died, and passed their material along to later generations. The idea was that structure took time, and that beauty required patience. Yet what Webb is showing us suggests the opposite. A universe that skipped the slow prelude and leapt straight into an advanced state. Instead of cosmic dawn, it feels like cosmic noon. And it is not only the brightness of these early galaxies that is shocking, it is also the speed and harmony with which they appear. They are not just too bright, they are too fast, too organised, and too numerous. Across the sky, Webb sees them not as isolated oddities, not as rare outliers, but as a whole population. They share features that suggest they were part of a larger coordinated process. They have advanced characteristics, disks, heavy elements beyond hydrogen and helium, and organised motions that should have taken far longer to emerge. To build such qualities, galaxies must go through cycles of star birth and star death, recycling material to enrich themselves with metals and heavier elements. But the timeline of the Big Bang model does not allow enough time for such maturity to appear so quickly. It is as though children have been born already grown, skipping the years of learning and growth and appearing before us as fully developed adults. The consequences of this are staggering. If this really is cosmic noon and not cosmic dawn, then our entire sense of time and sequence must be reconsidered. Perhaps what we have been calling the early universe is not early at all, at least not in the way we understood. Perhaps the Big Bang was not the first spark of creation, but only one chapter in a much longer story. Perhaps before the Big Bang there was already a universe well into its own cycle of growth and development, and what we are seeing is not a beginning but a continuation. The light we call first light might not be the birth of something new, but the return or rebirth of something older. Some scientists have long entertained theories of a cyclic or bouncing universe. In these frameworks, the cosmos does not begin and end in a single Big Bang, followed by a final collapse into nothingness. Instead, the universe goes through endless cycles of expansion and contraction. In these models, the Big Bang is not the start of everything, but a transition point, like the striking of a clock that marks the turning of an hour. Time does not begin at the chime, it merely moves into another phase. If the Webb telescope's discoveries hold true, they may give real observational evidence to these ideas. If galaxies are already thriving at redshifts higher than 12, then something must have come before them. Something must have seeded them with structure, giving them the conditions to form stars so quickly and to organise themselves with such elegance. This brings us to another concept: entropy. In physics, entropy is the measure of disorder. According to the rules of thermodynamics, entropy should always rise over time. That means things should become more chaotic, more disorganised, as the universe ages. At the very beginning, the cosmos was supposed to be hot, thick, and smooth, with little order. Over time, it should have grown more uneven, less structured. But what Webb is showing us looks like the opposite. In the early moments, instead of chaos, we see remarkable order. We see galaxies already organised, stars already in motion, heavy elements already present. This points to something strange. Either there is a kind of low entropy state we have not thought of yet, or we're seeing the memory of a previous cycle carried into this one. The order we are witnessing might not be new, it might be inherited. Some scientists are daring to suggest that maybe the light we are seeing now is not just early light but inherited light. This means the structures and patterns we see in the cosmos could be the result of processes that happened before the Big Bang. The galaxies shining so brightly now could be the children of an earlier universe, carrying the imprint of that older story into this new one. In that view, the cosmic dawn was not the first breath of the universe, but the reopening of a play after an intermission. The curtain rose again, but the stage was already prepared, the actors already dressed, and the drama already well underway. Of course, this is still speculation. The Webb telescope is young, and its discoveries are fresh. Ideas about what they mean are shifting rapidly, and debates among scientists are heated. But even so, the trend is unmistakable. There are too many bright galaxies, too many well-formed structures, too many surprising levels of maturity for the picture of a slow, patient dawn to hold. What Webb is showing us looks much more like a universe that was already awake, already bustling with life, already well into its story. This forces us to reconsider not only when the universe began, but also what a beginning truly is. If what we thought was the beginning turns out to be the middle, then we may have misunderstood the very shape of time. Maybe time itself is not linear, not a single arrow from past to present to future. Maybe it is circular, or layered, or something stranger than we can yet imagine. Maybe we're not reading the first chapter of the Book of Existence, but opening it halfway through without realizing there are pages before the ones we see. The James Webb Space Telescope, with its giant golden mirrors and extraordinary sensitivity, was built to look back to the earliest days of creation. And it has succeeded, but the picture it reveals is not the gentle sunrise we expected. Instead, it is a blaze, a fire already roaring, a cosmos already lit up and alive. This is both exhilarating and unsettling. Exhilarating because it shows us a universe more mysterious and rich than we ever dreamed. Unsettling because it means our oldest stories about beginnings may have to be rewritten. If time is playing tricks on us, if we're mistaking the middle for the beginning, then the story of everything is far stranger than we thought. Either time itself is lying, or we're holding the wrong book in our hands. Perhaps we're only now beginning to see how vast the mystery really is. For as long as human beings have been looking up at the night sky, they have wondered where everything came from and how it all began. The story of the universe has never been a simple one, and every age has shaped it differently. In the 20th century, the dominant explanation became what we now call the Big Bang theory, the idea that everything we see today emerged from a single, unimaginably small and dense state that exploded into space and time itself. Yet before this picture of the cosmos became the accepted one, there was another vision, one that captured the imagination of many great scientists and philosophers, and one that, even now, is beginning to echo again in the discoveries of the modern age. This was the steady-state theory. The steady-state idea was not just a minor footnote in science. It was a serious competitor to the Big Bang for many years. It was developed in the late 1940s by three men whose names became forever tied to it: Herman Bondi, Thomas Gold, and Fred Hoyle. These thinkers were not content with the idea that the universe must have begun at some definite point in time. To them, the suggestion that all of existence started with one giant flash, one single event, seemed not only unscientific but also strangely unsatisfying. They proposed instead a universe with no beginning and no end, one that stretched infinitely into the past and would stretch infinitely into the future. In their model, the universe was not static. It was expanding, just as observations already showed in those days, but it was expanding in a very particular way. As galaxies drifted apart and space stretched, new matter would continuously appear to fill the gaps. This did not mean that stars or galaxies simply popped into existence from nothing at once. Instead, tiny amounts of new particles would quietly be created, spread thinly across space, just enough to keep the overall density of matter in the universe constant. This way, the cosmos could expand forever without ever thinning out, and it could remain eternally the same on the larger scales. The appeal of this theory was not only scientific but deeply philosophical. Many people, including the scientists who created it, felt more comfortable with a universe that had no messy beginning. After all, if everything began with a single explosion, one could not help but ask, what happened before that? Why did it begin at all? Where did that initial point come from? The steady-state model neatly avoided all these troubling questions by saying that there was no beginning to speak of. The universe simply was, and always had been, and always would be. For several decades, the steady-state theory was a powerful rival to the Big Bang. Scientific debates raged, and both sides had their evidence. Supporters of the Big Bang pointed to the idea that if everything started from one point, then the universe should carry a trace of its fiery birth. Supporters of the steady state countered that what mattered was that the universe we saw looked essentially the same no matter where or when we observed it, and their model naturally provided that uniformity. But then, in the 1960s, came a discovery that seemed to slam the door shut on the steady-state dream. Two radio astronomers, Arno Penzias and Robert Wilson, detected a strange, faint glow of microwaves that filled the entire sky. It was not coming from any single source, nor was it caused by interference. It was everywhere, uniform and undeniable. This glow became known as the cosmic microwave background radiation, the faint afterheat of the birth of the universe. The Big Bang theory had predicted just such a leftover signal, while the steady-state model could not account for it in any convincing way. That discovery was like a final bell tolling for the steady state. From then on, the Big Bang became the dominant explanation, and the steady state was dismissed as a relic of outdated thinking. Most scientists moved on, considering the debate closed. The Big Bang, especially once combined with the idea of cosmic inflation in the early 1980s, seemed to explain almost everything. The expansion of space, the distribution of galaxies, the presence of the microwave background, the formation of light elements, and the large-scale structure of the cosmos. For decades, the Big Bang reigned supreme. It became not just the leading theory, but almost the only theory taught, discussed, and believed. The universe, according to this model, was around 13 and a bit billion years old. It had a fiery beginning, expanded rapidly, cooled, and then slowly gave rise to stars, galaxies, and planets. Black holes formed as massive stars collapsed. Galaxies assembled from smaller clumps, and over cosmic time, structure grew more and more complex. That was the story nearly every scientist accepted. But then came the James Webb Space Telescope, launched in the early 2020s. Webb was designed to look deeper into the universe than ever before, peering back to the earliest times when the first galaxies and stars were forming. What it revealed shocked many. The telescope's sharp eyes began to find galaxies so far away that their light had been travelling for nearly the entire age of the universe. Yet these galaxies looked far too big, far too bright, and far too organised for the early stages of cosmic history. According to the Big Bang model, they should have been messy, small and primitive. Instead, they looked mature, developed and complex. Webb also spotted stars that seemed to have levels of heavy elements, what scientists call metallicity, that should have taken billions of years of stellar generations to build up. But these stars appeared at a time when supposedly only the first pristine stars made of hydrogen and helium should have existed. Even more puzzling were the massive black holes, some of them containing millions or billions of solar masses, existing at times when the universe was supposedly only a few 100 million years old. According to the standard timeline, there simply had not been enough time for such enormous monsters to grow. It was as if the universe Webb was showing us was not young and chaotic, but already ancient and well organised, far earlier than it should have been. This picture began to whisper of something strange. Perhaps the universe had not begun so suddenly and recently after all. Perhaps, in some sense, it had been around much longer, ticking along steadily rather than rushing forward from a sudden start. The steady-state theory, long thought dead, began to look not quite so foolish. Not because Webb had proven it true, but because the cracks in the Big Bang model opened the door to thinking differently again. If the cosmos looked too old, too structured, too mature, maybe it really had more time than the standard model allowed, and that is precisely what steady-state offered. Infinite time. In a steady-state universe, there is no need to hurry. Galaxies can take as long as they want to form. Stars can slowly enrich their surroundings with heavy elements. Black holes can steadily grow without the need for frantic acceleration. Complexity does not need to appear out of nowhere. It can emerge gradually, forever, across eternal time. Of course, steady-state still faced its old problem, the microwave background. That faint glow of radiation has not gone away, and it remains difficult for steady-state models to explain. But even here, new ideas began to emerge. Some cosmologists wondered if perhaps the truth lay in combining the best parts of both models. What if the universe really had no single beginning, but instead went through cycles? What if the Big Bang we think of as the beginning was only the latest in a series of events, each one renewing the cosmos but not creating it from nothing? Fred Hoyle himself, later in life, along with colleagues, proposed a variation called quasi-steady-state cosmology. In this model, the universe was still eternal, but now it allowed for periodic creation events, sometimes called mini-bangs. These were not universe-wide beginnings, but local episodes scattered throughout the eternal framework, adding new bursts of matter and energy without ever requiring a single creation point. In the age of the James Webb Telescope, this does not seem nearly as far-fetched as it once did. Indeed, The galaxies Webb sees at high redshift, the very distant ones, do not look like the first galaxies ever formed. They look instead like the latest in a long line, as though they were born in a universe already rich with history. The stars inside them already contain heavy elements. The black holes at their centres are already massive. All of this makes more sense in a world that has been evolving for a very, very long time, not in one that suddenly sprang into being 13.8 billion years ago. There are also questions now about cosmic expansion itself. The Big Bang model assumes that the universe expands according to well-understood physics, at rates we can measure and predict. But recent measurements suggest otherwise. The expansion does not follow the clean, simple path that we once believed. Some data points to unknown influences, phantom energy, quantum effects, or something else entirely, that might be reshaping the cosmic timeline. If the universe expands more slowly than we thought, or if it expands in cycles rather than endlessly speeding away, then perhaps the early universe had far more time for structures to form. Again, this favours the long-haul realism of steady-state ideas. To be fair, most cosmologists today do not wish to return to the original steady-state theory exactly as Bondi, Gould and Hoyle imagined it. Too many observations, especially the microwave background, still argue against it. Yet scientists are beginning to dust it off, to re-examine its principles, and to wonder whether modern versions of it might hold clues. For whenever the current model begins to strain, when it must explain more and more anomalies while making fewer and fewer accurate predictions, it is natural to look again at alternatives. The story of cosmology is not finished. The Big Bang remains the reigning model, but it now faces challenges it cannot easily answer. The steady state, once declared dead, whispers again from the shadows. Perhaps the truth lies somewhere between, in a universe that is both ancient and renewing, both expanding and cycling, both changing and eternal. The James Webb Telescope, by opening new windows into the cosmos, has not ended the debate but reignited it. And so we find ourselves once more where Bondi, Gould and Hoyle once stood, asking the oldest question in new ways. Is the universe a story with a beginning, or is it a song without end? Was the universe truly born from an explosion, or could it have come from energy itself? This question has followed science for many decades, and it cuts to the heart of how we imagine reality. Most of the world has grown used to the Big Bang theory, which paints the picture of a hot and dense beginning, a single event where time and space themselves exploded into being almost 14 billion years ago. Yet, quietly in the background, another idea has always been present, an idea that dares to suggest the universe is not what we have been told. This alternative vision is called plasma cosmology, and instead of a bang, it begins with power. Plasma cosmology does not argue for a universe born from a singular moment of fire and noise. Instead, it describes an eternal universe, one without a clear start or a looming end. In this model, the engine that shapes the cosmos is not only gravity, which has long been considered the main sculptor of galaxies, stars and clusters, but plasma itself. Plasma is often described as the fourth state of matter, beyond solid, liquid, and gas. It is a soup of charged particles, electrons and ions, moving under the influence of electromagnetic forces. And those forces, the ones carried by electricity and magnetism, are staggeringly stronger than gravity. Electromagnetic forces can be trillions of times more powerful than the slow tug of gravity, and plasma cosmologists argue that this has been the real hidden architect of the universe all along. This model was shaped by the work of scientists such as the Nobel Prize-winning physicist Hannes Alpha Venn, who studied plasma in both laboratory settings and in space. He noticed that vast electric currents and enormous magnetic fields seem to flow across cosmic scales, linking stars, galaxies and clusters into networks. According to his vision, the universe is not a leftover fireball cooling in silence after an ancient explosion, but a grand and ongoing dance of charged matter, always flowing, always changing, always powered by electrical forces that never end. The contrast between the two pictures could not be more striking. In the Big Bang scenario, everything we see, the stars, the galaxies, the cosmic web, are the children of an ancient singularity that happened once and then expanded ever since. In plasma cosmology, there is no singularity. There is no moment when nothing suddenly became something. Instead, there is constant energy exchange, like currents in a cosmic ocean, with no true beginning and no absolute end. One of the most striking arguments in plasma cosmology comes from the way charged particles behave. In the traditional picture, galaxies are thought to form when clouds of hydrogen and helium gas collapse under their own weight, pulled together by the slow hand of gravity. This collapse takes millions, even billions, of years. But plasma physics tells a different story. In a plasma-filled universe, matter does not wait patiently for gravity to crush it. Charged particles respond to electric and magnetic fields, which can guide them, organize them, and pinch them together into long strands and filaments. These interactions are so strong that they can shape entire galaxies and star systems in far less time than gravitational collapse alone would allow. If we look at the actual maps of the universe created by astronomers, maps that show galaxies arranged not randomly, but in vast webs and strands across cosmic space, this looks strikingly similar to what plasma currents produce in experiments. Long filaments, great voids, spirals, and knots of matter are precisely what plasma currents form when they are channeled by magnetic fields. What if the large-scale structure of the cosmos is not the result of gravity slowly gathering scattered gas, but rather the visible trace of electric currents running across the universe? For many decades, this idea was dismissed. Plasma cosmology was brushed aside by most scientists, often ridiculed as unworkable or unscientific. It failed to explain some of the most famous features of the universe, such as the cosmic microwave background, the faint afterglow of radiation that Big Bang cosmology says is the leftover heat from the birth of the universe. Plasma cosmology also struggled to explain the relationship between redshift, the stretching of light from galaxies, and their distance from us. Big Bang cosmology could do both, so it quickly gained favour, while plasma cosmology was left in the shadows. But the story did not end there. With the launch of the James Webb Space Telescope, a new set of eyes opened on the distant past. Webb has been peering further and deeper than any telescope before it, and what it has revealed has unsettled even the most confident believers in the Big Bang model. Galaxies have been found that are too massive, too well-structured, and too mature to fit neatly into a universe that is supposed to have formed only through the slow pull of gravity in the short time available since the supposed beginning. Some of these galaxies already look like well-organized spirals, with dust, heavy elements, and even star-forming regions, when according to the Big Bang timeline, they should have been primitive and chaotic. But if one takes plasma cosmology seriously, these discoveries look far less surprising. Plasma physics allows for matter to clump, pinch, and organize itself far more quickly. For example, there is something called the Bennett pinch, named after a scientist who studied how electric currents could squeeze plasma together. In this process, magnetic fields generated by plasma currents can force charged particles into narrow strands, rapidly creating dense regions where stars can form. Instead of waiting for gravity to slowly collect gas clouds, plasma processes can ignite bursts of star formation quickly and dramatically. These bursts can create the complex elements needed for new stars and planets, spreading them widely across galaxies in a short time. The fact that James Webb is finding galaxies so early, so large, and so structured begins to look less like a mystery and more like an expected outcome in a plasma-driven universe. Plasma cosmologists even say that some of these results were predicted by their models long ago, not because plasma cosmology is magical, but because it builds on mechanisms that allow for speed and order, where the Big Bang model requires patience and long timelines. And remember, plasma is not rare. It makes up more than 99% of all visible matter in the universe. Stars, nebulae, and even the space between galaxies are dominated by plasma. If plasma is the rule rather than the exception, why would it not also be the main engine of cosmic creation? The galaxies revealed by James Webb are not just early, they are electrifyingly complex. Some are already arranged in filaments, strung together like beads on invisible cosmic wires. These embryonic versions of the cosmic web suggest large-scale order existed astonishingly early. Under gravity alone, such organization should have taken much longer. Under plasma cosmology, however, this is exactly what one would expect. Charge matter linked by vast electric currents naturally aligns into networks that resemble the cosmic web. Even the way we measure distance and time in the universe could be questioned if plasma plays a larger role. The Big Bang model interprets redshift, the stretching of light from distant galaxies, as evidence of cosmic expansion. The further a galaxy is, the more its light is shifted toward the red, because space itself is stretching as the universe expands. Plasma cosmology, however, suggests a different explanation. Photons, the particles of light, could be losing energy as they travel through plasma-filled intergalactic space. This gradual energy loss, sometimes called tired light, could mimic the effects of expansion without requiring space itself to be stretching. If that were true, then the galaxies we think of as being impossibly far and impossibly early may not be so distant or so ancient after all. Of course, plasma cosmology remains highly controversial. Most scientists still prefer the Big Bang model because it fits so many of the observations we have, and because it is supported by the powerful mathematics of general relativity and cosmic inflation. Plasma cosmology, in contrast, deals in messy, non-linear processes that are difficult to predict with equations. It does not have an easy way to explain the cosmic microwave background, and it has struggled to produce forecasts as precise as those of the Big Bang model. Yet some researchers are beginning to wonder whether plasma has been unfairly ignored. There is even a cultural story here. Plasma cosmology rose briefly in the mid-20th century, but it never became mainstream. It was not disproven outright, but it lacked the same institutional support and mathematical beauty that fueled the rise of the Big Bang. Big Bang cosmology offered clean equations, elegant relativity, and the dramatic simplicity of a single beginning. Plasma cosmology, on the other hand, offered messy laboratory experiments, unpredictable electric arcs, and chaotic systems. But maybe the universe itself is messy. Maybe the cosmos does not follow neat, elegant equations, but rather behaves like a storm of charged matter, organised in ways that look chaotic at small scales yet create order on the grandest scales. As James Webb continues to look deeper, peeling back layers of cosmic history, we may find that the universe is not simply the fading echo of a long-ago explosion. Perhaps what we're seeing is the ongoing pattern of a living electrical cosmos, structured not just by ancient beginnings but by constant forces, immediate and powerful, flowing through space even now. For almost one full century, the Big Bang has been the main story that scientists tell about how everything began. It has become the standard explanation taught in schools, written in books, and described in documentaries. According to this story, everything that exists, space, time, matter, and energy, was once packed into a single unimaginable point, a place smaller than anything we can picture, where the rules of normal physics break down. From this point, in an event described as an enormous explosion, the universe came into being. Time itself is believed to have started around 13.8 billion years ago, and ever since that beginning, the universe has been expanding, stretching out, and evolving into the vast cosmos we see today. This description has been powerful, elegant, and convincing. It has explained why the galaxies are moving apart, why space is filled with faint radiation left over from a hot beginning, and why the elements we know, hydrogen, helium, and traces of lithium, formed when the universe was still young. Yet, despite its success, some scientists have started asking whether this story is the complete truth. They wonder, what if the universe did not have a true beginning at all? What if time did not suddenly spring into existence, but instead has always been there, stretching endlessly backward and forward? This line of questioning leads into a very different idea, one that challenges the foundations of the Big Bang. It is called the Big Bounce. Unlike the Big Bang, which imagines a one-time creation from nothing, the Big Bounce suggests that the universe is part of a never-ending cycle. Instead of being born once and eventually dying in cold emptiness, the cosmos beats like a heart, expanding outward, slowing down, collapsing inward, and then bouncing back into expansion once again. This rhythm has no ultimate beginning and no final end. It is an eternal pulse that echoes across infinite time. In this vision, our universe is not the first. It is simply the latest in a long chain of universes, each born from the collapse of the last. The Big Bang was not the true beginning, but only the most recent rebound. Instead of a line that starts at a single point, reality is a loop circling around itself again and again. The idea is bold, but it is not new. For decades, scientists and philosophers have imagined cycles of creation and destruction, inspired both by ancient myths and by modern physics. What makes the Big Bounce especially interesting today is that the new tools of astronomy, particularly the James Webb Space Telescope, are beginning to show details about the universe that do not quite fit neatly into the Big Bang story. When the James Webb Telescope turned its golden mirrors toward the distant universe, it revealed galaxies that were far too large, too bright, and too organized for their age. According to the Big Bang timeline, the first galaxies should have taken hundreds of millions of years to gather, form stars, and shape themselves into structures. But Webb's observation showed massive galaxies already in place when the universe was supposed to be only a few 100 million years old. It was as if the universe had skipped some of its early steps and jumped ahead in its development. This is puzzling, but it makes more sense if the universe carries with it the memory of previous cycles. If the cosmos has been through expansions and contractions before, then the structures we see today might be leftovers, inheritances from an earlier universe that collapsed and then bounced. In that case, galaxies do not appear too soon. They appear exactly when they should, because they are not entirely new. They are shaped by the echoes of what came before. At the heart of the difference between the Big Bang and the Big Bounce is the problem of the singularity. In the Big Bang story, everything comes from a singularity, a place of infinite density and infinite temperature, where the laws of physics as we know them do not work. This singularity is not something scientists can truly explain. It is more like a placeholder, a way of saying, our equations stop here. For many, this has always been unsatisfying. How can science be built on something that cannot be described? The Big Bounce offers a way around the singularity. In this idea, the universe never actually shrinks to an infinitely small point. Instead, when the universe becomes very dense, strange effects from quantum physics take over. These quantum effects, acting like a pressure that resists collapse, prevent the universe from reaching a singularity. Instead, the universe stops contracting at a tiny but finite size and then bounces back outward into a new expansion. In this way, the singularity is erased. There is no need to imagine infinite density, because the bounce happens before that extreme is reached. This approach comes from theories of quantum gravity, especially something called loop quantum cosmology. In these models, space itself is made of tiny loops or grains, and just as matter cannot be compressed beyond a certain point, neither can space. When it is squeezed too tightly, the loops push back, and expansion begins again. Time, in this view, never ends. It simply changes direction, from contraction to expansion, and then back again, forever. The more scientists think about this, the more attractive it seems. Not only does it remove the mysterious singularity, but it also helps explain why the universe looks the way it does. For example, the cosmic microwave background, the faint afterglow of the early universe, is incredibly smooth, yet also filled with just the right amount of tiny fluctuations that grew into galaxies. In a one-time universe, explaining this balance is difficult, but in a bouncing universe, the structure might have been carried over from earlier cycles. The smoothness could be a result of long periods of contraction that even things out, while the fluctuations could be seeds inherited from a past expansion. If this is true, then the universe is not 13.8 billion years old as the Big Bang model says. It is far older, possibly eternal. It has always been here and always will be. Complexity does not need to have arisen quickly, because it did not arise from nothing. It has been here in one form or another for an infinite time, recycled and reborn with each bounce. This also changes how we think about the end of the universe. In the one-shot Big Bang picture, everything eventually runs down. Stars burn out, galaxies fade away, and the universe cools into a dark, empty void. This is the so-called heat death, where entropy, the measure of disorder, reaches its maximum and nothing more can happen. But in the bouncing universe, entropy may not build up forever. Instead, it could be reset or recycled with each bounce. Some models suggest that the collapse phase naturally clears out disorder, starting each expansion fresh. Others propose that entropy is drained into other dimensions, ideas borrowed from string theory. In either case, the bouncing cosmos avoids the final cold death. Instead of silence, it offers an endless heartbeat. Of course, the Big Bounce is not without its own challenges. One of the biggest questions is thermodynamics. If the universe bounces forever, does chaos keep increasing from one cycle to the next? If so, would each new universe be messier and less ordered than the last, eventually leading to a universe that cannot function? Some solutions suggest that every bounce makes the universe slightly bigger, spreading entropy more thinly each time. Others rely on exotic physics to handle the problem, These are open questions and scientists are still working on them. Another challenge is evidence. How can we prove that our universe bounced from a previous one? To test the idea, we would need to look for marks left behind. Fossils of earlier cycles imprinted in our own universe. These might show up as unusual patterns in the cosmic microwave background, as odd alignments or anisotropies that cannot be explained by a single Big Bang. They might also appear as subtle features in gravitational waves, the ripples in space-time created by massive cosmic events. Some cosmologists think that such clues may already exist, hidden in the data we have, waiting to be recognised. What today looks like noise or error could tomorrow be seen as the echo of an earlier universe. The search is ongoing, and the James Webb Telescope has already stirred the discussion by revealing galaxies that do not match the expected timeline. Each new discovery adds fuel to the possibility that the universe may be more complicated and more ancient than we ever imagined. To embrace the big bounce is to accept a universe without beginning or end, a cosmos that has always been alive with motion, always pulsing with cycles of death and rebirth. It is a universe where what we see today is shaped by what came before, and where what comes next will be shaped by us. The stars we see may carry the memory of countless earlier skies, and our own lives may be part of a rhythm that stretches beyond imagination. The Big Bang gave us the vision of a dramatic birth. The Big Bounce offers something even deeper, the vision of eternity. For more than 100 years, astronomers have trusted a particular tool to measure the great distances between galaxies scattered across the universe. This tool is called redshift. The idea is simple on the surface but profound in its consequences. When a galaxy is far away, the light it sends out must travel for millions or even billions of years before reaching our eyes or our telescopes. Over this immense journey, astronomers have noticed that the light does not arrive exactly as it was when it left. Instead, its waves appear stretched, shifted toward the red end of the rainbow of colours that we call the spectrum. The farther away the galaxy, the stronger this shift seems to be. To astronomers of the modern age, this pattern became so convincing and so deeply rooted in the framework of science that it was treated almost like a sacred truth. Redshift, they concluded, was evidence that the universe itself is growing, stretching like an inflating balloon, carrying galaxies away from one another. That growth, they said, is proof of the great beginning we call the Big Bang. But what if the story is not so clear? What if redshift does not automatically mean expansion? For all its elegance, what if the common interpretation of redshift has led us to accept an idea not because it is the only possibility, but because it became the most popular one? There exists another explanation, not new but rather old, born in the early 20th century and almost forgotten for decades. Now, with the incredible discoveries of the James Webb Space Telescope, this idea is quietly finding its way back into the conversation. It is known as the tired light hypothesis, and it paints a picture of the cosmos that is very different from the explosive and expanding one most of us have been taught. The tired light idea suggests that light does not become red because space is stretching, but because the light itself, made of tiny packets of energy called photons, gradually loses strength as it travels through the endless distances of the universe. Imagine a runner starting fresh and strong, then gradually slowing down mile after mile, not because the track is stretching under his feet, but because his energy is fading. In this view, photons are like those runners. As they cross the great ocean of space, they interact with the medium of reality in some subtle way that drains a bit of their vigour. Over countless years, this tiny loss adds up. Their wavelengths lengthen, sliding toward red, not because the galaxies are racing away, but because the light itself is aging. In this version of the cosmos, there is no grand expansion, no balloon of space inflating endlessly. Instead, the universe is ancient without beginning, perhaps infinite, and what we see as redshift is nothing more than the signature of tired light, light that has grown weary on its journey. It is not the universe that runs, it is the light itself that slows. The roots of this idea reach back almost a century. In the 1920s, a physicist named Fritz Zwicky suggested that the redshift astronomers observed might not be the result of an expanding cosmos at all. At the time, the idea of a universe that was stretching outward from a single beginning was just starting to take hold. Zwicky's suggestion was bold, even radical, because it went directly against the emerging picture of cosmic expansion. Yet it carried a kind of elegance, offering a simpler explanation. Light loses energy over distance, and that is all. But history did not favour Zwicky's thought. As the Big Bang Theory grew stronger in the public mind and in the halls of science, tired light was pushed aside. The expanding universe seemed to explain more of the data and became the dominant story. Tired light, on the other hand, was criticised. It did not account for certain observations, such as the way the light curves of distant supernovas stretch with time, or why galaxies far away remain sharp and not blurred if their photons were truly scattering and losing energy through interactions. Because the theory lacked a detailed physical mechanism for how light could lose energy, without smearing the image, it was labelled as incomplete and was left behind like an old tool no longer needed. Yet it never fully disappeared. Like an ember hidden under ash, the idea of tired light remained in the minds of a few, waiting for a gust of wind to bring it back to life. That gust arrived when the James Webb Space Telescope began sending its astonishing images to Earth. Webb revealed galaxies that looked far too mature for their supposed place in the cosmic timeline. According to the redshift model, these galaxies should have been seen as very young, barely formed chaotic clumps of matter. Yet Webb showed them as organised, structured, and old in appearance. Their stars seemed enriched with heavy elements, their black holes seemed already massive, and their shape suggested long histories of development. To many, this created a puzzle. If redshift means distance and time, then these galaxies appeared too evolved for how early in history they supposedly stood. Here is where tired light slips back into relevance. In the tired light picture, the redshift of those galaxies does not act like a clock. It does not tell us how early they are in the universe's story. It only tells us how much energy their light has lost in the long voyage to us. That would mean these galaxies are not impossibly young and mature at the same time. They are simply ancient galaxies whose light has been dimmed and stretched by distance. Their black holes are not premature giants. They are old, slowly fed monsters. Their stars are not against the rules of formation. They are signs of a universe that has existed for an eternity. Suddenly, many of the mysteries that seemed so troublesome under the Big Bang timeline dissolve like mist in the sun. Still, tired light has its critics. The question of sharpness remains one of the largest. If photons are losing energy through interactions, why do faraway galaxies look so crisp instead of fuzzy? Shouldn't those interactions scatter light like smoke in the air, blurring the details of distant objects? For decades, this was one of the strongest arguments against tired light. But new versions of the idea suggest subtler mechanisms, perhaps at the quantum level, where energy can leak in ways that do not blur the direction of the photon. Some suggest interactions with mysterious properties of the vacuum itself, invisible to us but real nonetheless, could allow light to tire without losing its clarity. These ideas are not yet proven, but they keep the door open for the hypothesis to remain alive. Another major challenge is the cosmic microwave background radiation. According to the Big Bang model, this faint glow is the leftover heat from the universe's hot and dense origin. It is seen today as a near-uniform bath of microwaves surrounding us from every direction. For the tired light model, this is a tougher puzzle. It does not naturally predict such a glow. Some supporters of tired light argue that what we call the cosmic microwave background could instead be explained differently. Perhaps it is not the echo of a fiery birth, but rather the steady accumulation of radiation from galaxies spread through infinite time, smeared and softened by distance. Or perhaps it is a background of light produced by processes we do not yet fully grasp, spread evenly across the cosmos. These are not complete explanations, and they remain speculative, but they show that the idea is not without paths to explore. What makes tired light especially compelling today is not nostalgia for old theories, nor the desire to be contrary, but the sheer precision of Webb's data. We are now able to see farther and with greater clarity than ever before. Each image Webb provides deepens the tension between the expected picture of a young, rapidly evolving universe and the reality of galaxies that appear too calm, too developed, and too rich in structure. The foundation of our cosmic timeline rests heavily on the link between redshift and distance, redshift and age. If that link is not as solid as once thought, then the entire chronology may be built on shaky ground. It may be that redshift tells us something real, but perhaps it is not what we have assumed. The reawakening of tired light, then, is not a matter of clinging to outdated science. It is an invitation to question whether we may have confused measurement with meaning. We measured the shift of light, and we assumed it must mean expansion. But what if it means something else? What if it tells us not that the universe is racing apart, but that light itself is mortal in its own way, subject to exhaustion across eternity? The James Webb Space Telescope is not designed to settle this debate. It was not launched to prove or disprove tired light. Yet by showing us galaxies that seem too advanced for their place on the Big Bang timeline, by revealing structures too orderly and black holes too massive too soon, Webb has breathed fresh life into old doubts. It has reminded us that even our most trusted interpretations are not untouchable truths, but human attempts to make sense of the vast and mysterious cosmos. Redshift may be a clue, but what it is a clue to remains a question not yet answered. And so we stand at a curious crossroads. On one path lies the familiar picture of a universe born in a blazing moment nearly 14 billion years ago, spreading outward, cooling, and giving birth to galaxies, stars, and planets as it grows. On the other path lies a universe without beginning or end, steady and eternal, where galaxies do not race away but simply exist, ancient and enduring, and where the light that reaches us carries the scars of its long journey in the form of weariness. The debate is not merely about physics, it is about the story we tell of existence itself. Do we live in a cosmos with a single dramatic birth, or in one that has always been, without origin? The cosmic microwave background, often shortened to the letters CMB, has for many decades been praised as one of the strongest pieces of evidence supporting the Big Bang story. Scientists have described it as the faint but ancient light that still fills the universe. It is, in fact, the oldest light that human beings are able to see with our instruments. This glow comes from a very distant time in the past, from the moment when the young universe had cooled down enough for the first atoms to form. Before that cooling, light particles, called photons, were constantly bumping into free particles like protons and electrons, making the cosmos thick and foggy. But once those particles combined into atoms, photons were free to travel unhindered through space, and that first release light has been moving ever since. We still catch it today, stretched into the microwave part of the spectrum because of the expansion of the universe. This steady afterglow was first noticed in the year 1965 quite by accident, when two engineers picked up an odd background signal with their radio antenna. It has often been called by poetic names: the afterglow of creation, the whispering echo of the beginning, or even a photograph of the baby universe, frozen in time about 380,000 years after the Big Bang. For generations, scientists have looked at it as a sacred picture, a snapshot of the earliest conditions of existence. But what if, despite all the reverence and confidence placed in it, we have been reading this picture the wrong way? The James Webb Space Telescope, which is one of the most ambitious space observatories ever launched, was not built to look at the CMB directly. Its instruments are tuned for the infrared part of the spectrum, not the microwaves where the CMB glows. Webb's task is different: to look at what came after the cosmic background, to gaze into the time when the very first stars and galaxies were being born. In doing this, Webb has become a kind of bridge, connecting that ancient frozen light of the background to the much more complex universe we see today. But this bridge, as strong as it was supposed to be, is beginning to show cracks. The difficulty is simple to state but profound in meaning. The CMB tells us how the early universe should have changed over time. Satellites such as COBE, Dalomap and Planck have mapped its tiny temperature differences in astonishing detail. These variations are unimaginably small, just 1 part in 100,000, but they are thought to be the tiny quantum ripples, the seed patterns from which every galaxy, every star and every planet would later grow. From these patterns we learned how much matter was in the universe, how clumpy or smooth it was at the start, and what types of structures we should expect to appear at different ages. Yet James Webb is now showing us something unexpected. It is seeing more structure, more complexity, and far larger cosmic objects much earlier in time than the theories based on the CMB predicted. That is not a small problem. If the CMB is really the picture of the initial conditions, then how did the universe assemble itself so quickly and with such order? It leaves us with two uncomfortable possibilities. Either we do not truly understand how matter grew from those ancient seeds, or perhaps the CMB itself does not give us the full story after all. One troubling issue has always been the scale of the fluctuations. As mentioned, the CMB is remarkably smooth, with temperature variations no greater than 1 part in 100,000. Such smoothness has always been a puzzle. If matter was spread so evenly, then by all normal calculations it should have taken an immense amount of time for it to clump together into stars, galaxies, and the vast cosmic webs we see today. To solve this, scientists introduced the idea of cosmic inflation. Inflation proposes that the infant universe expanded at an unbelievably fast rate, stretching everything out until it became smooth, but leaving just enough tiny imbalances behind for structure to grow. But Webb's discoveries complicate this neat picture. The early galaxies it has revealed look too massive, too developed, and they appeared too soon. It is as though the cosmic seeds were larger than expected, or as if they grew far faster than the CMB suggests they should have. This forces us to consider two unsettling possibilities. Either the growth of structure took place independently of the patterns in the CMB, or else the conditions we thought were present at the very start were not the real ones. Another problem arises from the sameness of the background. The CMB is said to be isotropic, which means that it looks essentially the same in every direction of the sky. This has always been taken as proof that the universe, on the larger scales, is uniform. Yet Webb has found areas of the sky with unusually high numbers of very early galaxies. If that is true, then either the CMB failed to capture some local variations, or the grand idea that the universe is the same everywhere on large scales may be flawed. If the young cosmos was not as smooth as the CMB portrays, then something must have happened between the release of the background light and the birth of the first galaxies, or else the CMB itself is not a reliable record of the past. The deeper worry is that perhaps we do not truly understand the CMB at all. Some alternative models of the universe suggest that the microwave background is not a leftover from a fiery Big Bang beginning, but something else entirely. In versions of quasi-steady-state cosmology, or plasma cosmology, the background is seen not as the glow from creation, but as an equilibrium radiation. In this view, it would be made up of light and energy from countless stars, galaxies, and black holes that, over unfathomable ages, have been stretched and redshifted into the microwave spectrum, giving the illusion of an ancient cosmic glow. Even within the Big Bang framework, problems remain. One of the most persistent is known as the Hubble tension, the stubborn difference between two measurements of how fast the universe is expanding. When the rate is measured using the CMB, it gives one number, but when it is measured using nearby galaxies and other local markers, it gives another. The two values do not agree, and the gap has not gone away. In fact, data from Webb is making the local measurement even more precise, which only sharpens the tension. That means something in our early universe predictions derived from CMB physics may not be right. It suggests that the very structure of space and time could be more complicated than what we currently imagine. The James Webb Space Telescope was not meant to measure the CMB directly. Yet by observing how the cosmos actually evolved from that supposed starting point, it has become a mirror. It reflects not only the predictions that the CMB has given us, but also the cracks, the uncertainties, and the possible mistakes in our understanding. In this way, Webb is forcing us to ask whether the afterglow of creation is really telling us the full truth about the beginning of everything, or whether it is only part of a much larger, more mysterious story. In the grand story of the universe, scientists once thought that the very first stars would be simple and straightforward. These first stars, often called population 3 stars, were imagined as enormous, short-lived, and, most importantly, completely free of metals. When astronomers use the word metals, they don't mean shiny materials like iron bars or silver coins, but instead they mean any element heavier than helium. This is because, in astronomy, the simplest building blocks, hydrogen and helium, came straight from the Big Bang itself, but everything heavier, like carbon, oxygen, iron, or gold, was created much later inside stars. Stars forge these heavier elements in their burning cores through the process of nuclear fusion, and when the biggest stars die in powerful explosions called supernova, they scatter those elements across the universe. But here's the catch. At the very beginning, those metals had not yet been made, so naturally the first stars could not have contained them. They should have been made only of hydrogen and helium, the purest materials left behind after the birth of the universe. Scientists thought of these first stars almost as blank pages in a book, waiting to be written on by the fires of fusion. For a long time, this picture seemed logical and neat. Metals became, in a sense, the marks of time. The more metals you find in a star or galaxy, the more generations of stars must have come before it to create those metals. If you imagine the universe as a clock, metals are like the ticking seconds, showing how much time has passed. But then came the James Webb Space Telescope, which can peer deeper into the past of the universe than anything we've ever had before. What Webb found shook the very foundations of this tidy story. As it looked farther back, towards the time when the universe was only a few 100 million years old, it discovered galaxies that were surprisingly rich in metals, not just a little rich, but in some cases containing as much or even more metal than our own Milky Way galaxy, which has had more than 13 billion years to enrich itself with countless generations of stars. This discovery was shocking because by the rules we thought we understood, there simply wasn't enough time for so many stars to be born, live out their fiery lives, die, and scatter metals across the cosmos in such a short period. Multiple generations of star birth and death should not have been able to fit into those first few 100 million years. And yet, there they were, galaxies glowing with chemical fingerprints that, by all expectations, should not belong in that era at all. This isn't just a small puzzle, it directly challenges the way we have long believed stars and galaxies grow and evolve. For decades, scientists assumed that the first stars would burn very hot and very fast, then die in explosions that created the very first carbon, oxygen, iron, and other metals. Only after this process repeated itself several times across many generations would galaxies rich in metals appear. But Webb is showing us something altogether different. Metal-rich galaxies existing not only early, but also spread widely throughout the young universe. These aren't odd outliers or freak exceptions. They appear to be whole populations of galaxies with high chemical complexity, far earlier than our models allowed. The problem isn't just the presence of metals. The real problem is what it implies. It suggests that either stars and galaxies evolved much faster than we thought possible, or perhaps they didn't evolve in the way we thought at all. Maybe the first stars were so massive and so unstable that they lived and died even faster than anyone imagined, enriching their surroundings with heavy elements in mere tens of millions of years. But for that to work, the process would have had to be unbelievably efficient, with enormous stars forming almost immediately after the Big Bang, exploding in well-timed waves and sparking new waves of star formation in rapid succession. It's not impossible, but it begins to sound like a dance whose choreography doesn't quite add up. And then comes an even stranger possibility. What if these metals weren't made after the Big Bang at all? What if they were already there, carried over from a universe that existed before ours? Some theories, like cyclic cosmologies or the so-called Big Bounce, imagine that our universe is not the first, but just one of many. In such ideas, the universe could collapse and then rebound, starting anew while carrying forward traces of the previous cycle. In that case, the metals Webb is detecting in these early galaxies may not be early at all. They might be survivors from an older world, relics of a cosmic history far deeper than we ever dared to think. Suddenly, those premature metal-rich galaxies don't look too young. They look ancient, experienced, like veterans of an earlier universe reborn into this one. And there is another unsettling question. What if population 3 stars, those supposed first metal-free giants, never even existed? Astronomers have been searching for decades, yet not a single truly metal-free star has ever been found. Not in nearby galaxies, not in the most ancient corners of the Milky Way, not even in the farthest galaxies Webb can see. Every star we have ever studied has at least some trace of metals. It could mean that population 3 stars were so rare and so short-lived that they vanished without leaving a trace we could detect. Or it could mean something far more dramatic, that our entire understanding of how the universe's chemical elements came to be is flawed. Webb's extraordinary sensitivity allows astronomers to read the spectral lines of distant galaxies with unmatched clarity. These lines act like chemical signatures, spelling out which elements are present. And what they reveal more and more often is a story that does not match the predictions of standard Big Bang nucleosynthesis, the theory that explains how the first light elements formed. The deeper we look into the cosmic past, the clearer it becomes that metals seem to be woven into the fabric of the early universe itself. It's as if ink appeared on the pages of a book, even before the printing press was invented. So what are we supposed to do with this strange truth? We could try to adjust our models, imagining scenarios where stars formed with almost unimaginable speed and efficiency, or even reconsider what we mean when we call something early. But with every adjustment, a model once praised for its elegance and simplicity becomes more stretched, more complicated, and harder to believe. Or we could face an even deeper possibility, that the universe's chemical story is not clean, not simple, and not as young as we thought. Perhaps galaxies, stars, and even black holes are whispering to us about something older than the Big Bang itself, about a hidden past that stretches further back than the timeline we have built. If that is the case, then Webb is not just showing us a younger universe. It is showing us an older truth, one that suggests our cosmic story is not a straight line from a single beginning, but something far richer, stranger, and more mysterious. It was once thought that the earliest times of the universe would be simple and straightforward. After the great burst of creation we call the Big Bang, the newborn cosmos was expected to cool and settle into a vast, silent ocean of hydrogen and helium gas. These two elements, the lightest and simplest of all, had been forged in the very first few minutes of cosmic nucleosynthesis, when the young universe was still unimaginably hot and dense. For hundreds of millions of years afterward, nothing dramatic was supposed to happen. Gravity had not yet pulled matter into clusters, stars had not yet ignited their fiery furnaces, and no stellar deaths had scattered heavier materials into space. The universe drifted through a long, hushed interlude known as the Cosmic Dark Ages, a time when no new chemistry unfolded and everything remained still and unchanged. That was the story scientists once believed, but the discoveries of modern instruments, especially the James Webb Space Telescope, along with other highly sensitive observatories, have begun to unravel that simple picture. Astronomers are now finding immense, ancient clouds of gas so far away that their light has travelled more than 12 billion years to reach us. These clouds, which may date back to the dawn of time, are proving to be anything but simple. Their temperatures, their densities, their chemical makeups, and even their shapes all raise unsettling questions about the early history of the universe. The first problem concerns their chemical composition. According to the traditional Big Bang model, these clouds should contain nothing but pure hydrogen and helium. Heavier elements, what astronomers call metals, including carbon, silicon, and iron, can only be created inside stars and then spread through space by stellar explosions. Yet, puzzlingly, some of these supposedly untouched primordial gas clouds already show traces of those heavier elements. If that is true, then either an entire generation of stars must have existed earlier than we imagined, leaving behind their ashes, or else our timeline of cosmic history is fundamentally flawed. Perhaps these clouds are older than we think, their true age hidden behind the way their light is shifted across space. Their temperatures and densities bring even more confusion. A number of the clouds are strangely cold, as though they had somehow reached thermal stability far earlier than expected. Others are unexpectedly hot and dense, almost as if some mysterious source of energy were pressing upon them. Could invisible magnetic fields stretching back to the universe's first moments be involved? Could there be leftover heat from a cycle of existence before the Big Bang? These are exotic ideas, far outside the ordinary tools of standard cosmology, but the observations force astronomers to keep the questions alive. Even more striking is their structure. In the earliest universe, gas was believed to be spread out in a nearly even haze, disturbed only by the faintest ripples imprinted during inflation. Gravity would then slowly tug on these ripples over time, gradually gathering gas into filaments, clusters, and galaxies. But some of the gas clouds now being seen are already clumped, filamentary, or even rotating, features that suggest they are much further along in their evolution than they should be. It is as though they are skipping steps, forming shapes and patterns, long before gravity should have had the chance to mould them. This strangeness has even led some scientists to re-examine the very foundation of how we measure cosmic time. Redshift, the stretching of light into longer, redder wavelengths as the universe expands, has long been treated as a reliable clock. The higher the redshift, the older the light. Yet if these clouds are not as young as their redshift suggests, then something unknown may be distorting our cosmic measurements. Perhaps the universe is tricking us in ways we do not yet understand. The locations of these clouds only deepen the mystery. They do not always appear where astronomers expect them to be. Some are isolated in empty regions of space, unconnected to any galaxies or star-forming regions we can see. Others seem misplaced, as though they belong to structures invisible to our telescopes. Their sheer remoteness makes it nearly impossible to say what they truly are. Could they be fragments of galaxies that never fully formed? Could they be the halos of proto-galaxies, waiting to evolve into something greater? Or are they strange relics of a hidden chapter of cosmic history that we have never considered? A far more unsettling possibility has also emerged. What if some of these gas clouds are not from our universe at all, but remnants from a universe before ours? Certain cosmological theories imagine cycles of creation and collapse, worlds that are born, die, and are reborn in an endless loop. If so, then perhaps these clouds are fossils of a previous universe, fragments carried forward into the present cosmos. If true, that would mean the evidence of an earlier world is floating in our skies, written in chemical traces and ghostly structures that defy the idea of a single beginning. Mainstream astrophysics is not ready to leap to such a bold conclusion. Most researchers prefer to search for explanations within the established model, yet the contradictions are piling up, and the gas clouds will not be easily explained away. They are not pure, not even, not inert. They appear already touched by history, already shaped, already enriched. It is as if they remember events that, according to our story of the cosmos, should not have happened yet. The standard tale of cosmic evolution has always been one of simplicity building into complexity. First, there was hydrogen and helium. Then came the first stars, then the first galaxies, and only after long ages did the richness of elements, structures, and diversity appear. But these clouds do not follow that ladder. They arrive as if the end were already hidden inside the beginning. They are complex when they should be simple. They are evolved when they should be raw. They force us to confront the most haunting of questions. What came before the beginning, and how much of it still lingers in the skies above us? For as long as human beings have looked up at the night sky, a troubling question has refused to go away. It whispers from the stars, it haunts the silence between galaxies, and it burns in the minds of scientists, dreamers, and storytellers alike. Where is everyone? This haunting question is at the heart of what is called the Fermi paradox. On the surface, it is simple. The universe should be full of life, yet we see and hear nothing. The odds of other civilizations existing seem incredibly high, yet the silence of the cosmos is absolute. Every galaxy contains not thousands, not millions, but billions upon billions of stars. Many of those stars are far older than our Sun. If planets circle those ancient stars, then intelligent life should have had an immense head start. Whole civilizations might have had time to rise, grow, and scatter their traces across space. We should see the marks of their journeys, signals, machines, or at the very least ruins drifting in the dark. But instead, what greets us is a vast, unbroken stillness. And now, with the James Webb Space Telescope piercing the fog of cosmic history, the mystery has only deepened. Webb has shown us things we did not expect. Galaxies already mature, stars and structures forming far earlier than we once believed, and hints of complexity in the universe's childhood. If order and structure emerged so quickly, then the possibility of life may also have appeared billions of years before Earth was even born. In that case, our world may not be a pioneer, it may be a latecomer. Imagine civilizations already ancient and fallen long before our planet cooled from fire into stone. The famous Fermi equation once asked whether life might exist elsewhere, but the question has shifted. The evidence we now gather suggests that there was more than enough time, perhaps countless ages, for intelligent life to appear, expand, and even transcend its beginnings. The fact that we hear nothing does not mean there was never anyone there. It could mean that something much darker and more mysterious prevents us from hearing them. Some scientists wonder if we are simply separated by the cruel laws of the cosmos. The universe itself is expanding, and dark energy is pushing galaxies apart faster and faster. With every passing moment, distant worlds are slipping further away from us. Not only is it unlikely that we could travel such distances, it may be physically impossible. Civilizations may have thrived, but the fabric of space itself might have locked them into lonely islands, forever beyond reach. Another chilling possibility is that civilizations do not endure. Perhaps they burn brightly for a short time and then collapse under their own weight. The same rapid processes that let galaxies grow young may also prepare the stage for destruction. If intelligent life appeared early, maybe it destroyed itself long before it could invent ways to cross the stars, and the more advanced a society becomes, the greater its power to erase itself, whether through war, runaway machines, poisoned environments, or catastrophes of its own making. There is also the unsettling idea that civilizations may not vanish at all, but instead transform. Imagine beings so advanced that they no longer cling to physical reality. They could abandon bodies of flesh and worlds of matter, choosing instead to live within digital realms, quantum networks, or even entirely new universes of their own design. To them, the universe we see, the galaxies and stars that amaze us, might seem no more meaningful than a forgotten wilderness beyond the walls of their shining digital cities. If that is the case, then we are staring at an empty stage, not because it is truly empty, but because the actors have already moved somewhere we cannot follow. The revelations from Webb do not disprove these haunting possibilities, they make them more believable. By showing us that the cosmos reached order and complexity so swiftly, Webb has stretched the timeline of possible life, and in doing so stretched the history of silence. And then comes an even heavier thought. What if other beings are reaching out, but we are too primitive to notice? Their signals might not be the crackle of radio waves or the glow of enormous buildings. Their fingerprints could be hidden in the strange bending of light, in the delicate lace of quantum entanglement, or in tiny shifts of the cosmic background itself. If we struggle to understand what Webb shows us about galaxies and stars, how could we possibly recognize the work of minds that are billions of years older and wiser than ours? Yet there is, at the end of this dark trail of questions, one last possibility, perhaps the most extraordinary of all. What if we are not latecomers, but pioneers? What if life is so rare that we, fragile and flawed though we are the first ones to stand in a universe just beginning to awaken? Webb may reveal that the cosmos organized itself quickly, but that does not prove that life followed. Perhaps stable, life-friendly worlds are uncommon. Perhaps intelligence is not an inevitable outcome, but a rare accident. If that is true, then we are the very first voice to speak in a quiet universe. That voice, our voice, may one day fade into silence, lost among the stars. Or it may become the seed of a conversation that will last for ages beyond imagination. Either way, the silence above us is not an answer. It is an invitation. The thought that the universe had a beginning is one of the greatest and most powerful ideas in all of modern science. For centuries, people wondered if the cosmos had always existed, or if it had a first moment, a kind of cosmic birth. The Big Bang Theory gave an answer. It told us that everything we see around us, time itself, space itself, and all the matter and energy that fill them, burst into being in one single extraordinary event. It was not just an explosion in space, but the sudden appearance of space and time themselves. In a sense, the Big Bang gave us a cosmic clock. It gave us a starting line, a way to measure history, a moment we could study, test, and build models around. What was once a mystery locked in philosophy and private thought became something science could talk about in public. And yet, the more deeply we look into the skies with our modern telescopes, the more puzzling things become. The farther out into space we look, the farther back in time we're peering. In theory, we should be seeing a young universe still taking its first steps, galaxies only beginning to form, stars still in their infancy, and black holes just starting to emerge. But what do we actually see? We see galaxies that are already large and well-structured. We see stars that are already filled with heavy elements like carbon, oxygen, and iron. Metals that take generations of stars to forge. We see massive black holes sitting proudly at the centres of galaxies when, according to the timeline, they should not have had enough time to grow so large. Instead of a baby universe, we're staring at a cosmos that looks oddly mature, as though it has already lived through untold ages. This raises deep questions. In classical physics, the idea of a beginning creates a hard boundary. It is like drawing a line on a map and saying, beyond this there is nothing. The Big Bang singularity is exactly that line. It is described as a point of infinite density, infinite temperature, and infinite energy, numbers that make no sense to our science. At that moment, time itself begins at zero. There is no before to talk about. But is that really science? Or is it simply our way of saying, we do not know, and then covering it with equations? Some thinkers say the Big Bang singularity is not so much an explanation as it is a confession of ignorance, a gap in our knowledge dressed in mathematics. That is why alternative ideas once ignored or laughed at are now being taken more seriously. Some cosmologists believe that the Big Bang was not the beginning of everything but a transformation, a shift in state, like water turning into ice. In this view, the universe may have existed in another form before the Big Bang, perhaps filled with strange quantum fields or even higher dimensions that collapsed into the form we know today. Others suggest that the universe never began at all, but is eternal, endlessly cycling through phases of growth, collapse, and rebirth. The cosmos may be like a beating heart, or like a phoenix that never truly dies, but always rises again from its ashes. There are also bold new ideas from the field of quantum gravity, which tries to unite the laws of the very large, Einstein's relativity, with the laws of the very small, quantum mechanics. Some of these ideas suggest that space and time themselves may not be fundamental at all. Instead, they may be emergent, like patterns that appear on the surface of water, even though the water itself is made of smaller molecules. If this is true, then asking when time began might not even be a meaningful question. It would be like asking when the smooth surface of a lake was born, while ignoring the billions of tiny water molecules underneath. What pushes these radical ideas forward is not only theory, but also the mounting evidence that does not fit neatly into the Big Bang picture. The James Webb Space Telescope, for example, has revealed galaxies that are far too massive, far too developed, and far too chemically advanced for a universe that is supposed to be in its infancy. The large-scale cosmic web of matter that links galaxies together looks too organised too soon. The stars look too mature, their chemical fingerprints too rich. These are not small cracks in the story. They shake the very timeline we thought we understood. So what would it mean if the universe had no beginning? It could mean that the cosmos is not a story with a first chapter, but rather an endless engine, always changing its shape, always turning over, without ever starting or stopping. It could mean that time itself is only a local illusion, something that exists from our point of view but not in the deepest layers of reality. In the most extreme ideas, the universe is not moving through time at all, but is a block of existence where past, present and future are all equally real. In that picture, our sense of flowing time and beginnings is just the way our minds perceive reality, not reality itself. This opens up ancient questions once again. Do we need the idea of creation at all? Is life and existence something that must have a cause? Or are we like fish swimming in the sea, unable to imagine anything beyond the water that surrounds us? Maybe beginnings and endings are ideas our minds create because we live in a world where everything seems to have them. Birth and death, sunrise and sunset. But the universe itself might not follow those same rules. None of this means the Big Bang is wrong or useless. Far from it. The Big Bang theory remains the most powerful and reliable framework we have for explaining many features of the universe. It explains the faint afterglow of radiation, the cosmic microwave background that fills the sky. It explains why space is still expanding. It explains why the universe is full of light elements like hydrogen and helium. These are powerful successes, and yet we must ask, was the Big Bang truly the beginning of all things, or was it simply the beginning of what we can see? Long ago, philosophers believed that the universe was eternal and perfect, a grand machine that had no start and no end. Then, with the rise of the Big Bang theory in the 20th century, the cosmos was given a birthday, a first cry, a beginning. But now, as new evidence comes to light, we may be circling back to the old thought again. Perhaps the universe never truly began. Perhaps it has always been here, in one form or another. Perhaps the cosmos itself is timeless. For more than 100 years, people have used Albert Einstein's picture of the universe to guide them. His theory of relativity describes the cosmos as a great four-dimensional fabric, a kind of invisible cloth made of space and time woven together. In this picture, heavy objects like stars, planets, and black holes press down on the fabric, bending it. That bending tells other things how to move, the way a ball rolls if you place it on a stretched blanket and put a weight in the middle. Space shapes the path of matter while time ticks onward like the steady hand of a cosmic clock. What is remarkable is how well this model has worked. Long before we could see them, it told us that black holes must exist. Long before we could detect them, it said gravitational waves must ripple through the universe. With its help, astronomers have drawn maps of distant galaxies, charted the twisting paths of stars, and even guided spacecraft with astonishing precision as they journeyed across the solar system. But now, in the 21st century, a new tension is growing. The James Webb Space Telescope, launched in the year 2021, has opened humanity's eyes wider than ever before. It lets us see the farthest and oldest galaxies, almost back to the dawn of time. And what we are finding is puzzling. So puzzling that it makes us wonder whether space and time themselves are what we think they are. The more we look, the more the universe begins to act in ways that do not fit neatly into Einstein's fabric. We see galaxies forming far faster than space-time should allow, and stars that appear fully grown before the cosmic clock should have given them enough years. We find structures that seem to appear before the stage on which they are supposed to exist. These surprises hint that our trusted model may not be the whole story. At the heart of this puzzle is a daring idea from the strange world of quantum physics. What if space and time are not the deepest layer of reality at all? What if they are illusions, like mirages on the desert road, useful, convincing, but not fundamental? Some physicists now believe that space and time may emerge from something deeper, the way temperature is not a single object but arises from the countless motions of molecules, or the way a hologram creates a three-dimensional picture from flat patterns of light. In this view, time may not truly flow, and space may not truly stretch. Instead, both could be rough impressions, shadows of something hidden beneath, built from building blocks we do not yet have the language to describe. This is not just idle philosophy. It grows from real scientific theories, ideas like causal set theory, loop quantum gravity, and emergent gravity. These suggest that space-time is not continuous but made up of smaller parts, tiny grains of information linked together in invisible webs. If this is right, then what we see through telescopes may not be showing us space and time as they really are, but only the surface effects of a deeper code. Even the way we measure the universe might need to change. Today, the main tool astronomers use is redshift, the stretching of light toward the red end of the spectrum as galaxies race away from us. This stretching is explained by the expansion of space itself, but if space is not really stretching, or not stretching in the way we think, then our whole picture of the universe's size could be wrong. Perhaps galaxies we believe to be 13 billion light-years away are not so distant after all. Perhaps they exist in a kind of hidden location, not far away, in the usual sense of space. Quantum entanglement gives us a clue. This strange phenomenon shows that two particles can act as though they are side by side even when they are separated by light-years. Some physicists think this is no accident. It may be a sign that distance is not real in the way we think. In a deeper reality built from information, 2 points may be close if they are linked, no matter how far apart they look in our universe. If this is true, then space is not absolute. It is not a rigid stage with fixed coordinates, but a web of relationships, where closeness depends on connections, not on miles or light years. Time, too, is slippery. In the old physics of Isaac Newton, time was absolute, the same everywhere. In Einstein's relativity, it became flexible, stretched by speed and bent by gravity. But in quantum theory, time hardly appears at all. It is not a fundamental part of the equations, but a parameter we impose to make sense of events. In some ideas of quantum gravity, time does not exist in any form. Things simply are, all at once. What we call change, motion, or cause and effect may be only the story our minds tell when moving through this timeless network of relations. If James Webb keeps showing us galaxies that seem to be older than the universe should allow, or cosmic structures that appear before there was time to form them, we may be forced to accept a more radical idea. Perhaps the universe does not run on space-time at all. Perhaps space-time is the shadow, and the real machinery is hidden beyond. The cracks are already showing. Many researchers are turning to the holographic principle, the daring suggestion that all the information in the universe is stored on a vast cosmic surface, like a three-dimensional picture painted on a flat wall. Black holes, with their mysterious information-packed surfaces, hint at this. Quantum entanglement hints at this. Even dark energy, the unknown force driving the universe's accelerated expansion, might be a clue. Together, these signs whisper the same possibility, that space-time is a trick and the true currency of reality is information. We have known about gravity longer than any other force in the universe. It was the very first fundamental force that people noticed, because it touches our everyday lives so clearly. An apple falls from a tree, a ball rolls down a hill, the moon circles the earth, and the earth circles the sun. All of these motions are ruled by gravity. Centuries ago, Sir Isaac Newton explained gravity in simple but powerful ways, using apples and circles to describe how it works. Then, much later, in the early years of the 20th century, Albert Einstein completely changed how we understood it. He showed that gravity is not really a force pulling at things from a distance, but rather the bending and curving of space and time itself. Galaxies are stitched together by gravity's invisible threads. Stars and planets spin and dance under its grip. Black holes, the strangest objects in the universe, are pure monuments to gravity, where it becomes so strong that not even light can escape. And yet, for all its greatness, gravity remains one of the most puzzling mysteries in the world of science. It is unlike the other forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. Those three forces are well described by quantum physics, the strange branch of science where uncertainty, entanglement, and probabilities rule. But gravity does not follow the same rules. It resists unification. It refuses to fit into the quantum framework, almost as if it plays by an entirely different set of laws. This mismatch between Einstein's smooth picture of gravity and the jittery, unpredictable world of quantum mechanics becomes most urgent in extreme places. In the very first moments after the birth of the universe, during the Big Bang, or in the crushing heart of a black hole. Traditional physics breaks down there. Equations stop making sense, and infinities appear like mathematical screams that something deeper is missing. Now, telescopes like the mighty James Webb Space Telescope are giving us a reason to revisit this problem. Webb may not be able to directly detect quantum gravity, but its discoveries are forcing scientists to look again at this elusive frontier. The telescope has seen galaxies forming far too early, stars becoming enriched with heavy elements far too quickly, and massive structures appearing without the scaffolding that normal physics predicts. These puzzling signs suggest that perhaps something deeper is at work, a hidden law of nature that we have not yet uncovered. This is where the quest for quantum gravity begins. At its heart, it is the effort to bring together Einstein's general relativity, which explains the cosmos on the larger scales, with quantum mechanics, which rules the tinier scales. The goal is to explain how gravity behaves when things are unimaginably small and impossibly energetic, like in the first instant of creation or in the core of black holes. But when scientists try to mix the two sets of rules, chaos erupts. Einstein's equations describe smooth, continuous space-time. Quantum mechanics insists on fluctuations, uncertainty, and little packets of information. When combined, the math spits out nonsense, infinities, contradictions, and models that collapse under their own weight. So new ideas have been born. Some thinkers turn to string theory. In this vision, the tiny building blocks of reality are not points but vibrating strings, living in as many as 11 dimensions. These extra dimensions may be hidden from our senses, curled up so tightly that we cannot see them. But if real, strings could unify all forces of nature, including gravity. String theory even allows for brains, vast higher dimensional walls that might hold entire universes like bubbles in a cosmic sea. This idea even opens the door to strange pictures of the cosmos, parallel universes, endless cycles of cosmic births and deaths, and realities beyond our imagination. Others have turned to loop quantum gravity. This theory goes in the opposite direction. It says that space is not smooth at all, but made of tiny, discrete chunks, like dots on a computer screen. According to this idea, the universe is woven out of an invisible network of quantum loops, forming a grainy mesh. Time itself is not a smooth river, but shifts in step with this quantum network. And perhaps most striking of all, the Big Bang may not have been the beginning of everything, but rather a bounce, a moment when a previous universe collapsed and then transformed into the one we see today. These are not just wild fantasies or games of mathematics. They can be tested. If space and time themselves are born from quantum processes, then the early universe should carry quantum fingerprints. Strange irregularities, odd patterns in how galaxies form, or unusual ways that light travels across the cosmos could all be signs. And some of what James Webb has already seen, galaxies too mature, structures too early, might be exactly those kinds of hints. Even the smoothness of the universe, which scientists once explained by a rapid burst of expansion called inflation, might instead be explained by quantum connections. In some models, entanglement itself, the deep quantum link that ties particles across vast distances, could have stitched the early universe together in a pre-geometric state, before distances or directions even existed. In that picture, everything was linked, and causality as we understand it today did not apply. A radical idea also emerges. Information may be more fundamental than matter or energy. Patterns of quantum entanglement could actually shape the geometry of space-time itself. From this point of view, the universe is not expanding into space. The universe is the process of space and time being woven from quantum information. The cosmos becomes something like an enormous quantum computer, turning data into the physical reality we live in. This means that when James Webb peers into the distant past and sees galaxies that are too complete, or black holes that appear too close to the beginning of everything, the problem might not lie in the telescope or the data. Instead, it may be revealing a hidden truth, that space, time and gravity are not the foundations of the universe, but the outcomes of something deeper. They are not the rules, but the effects. They are echoes of quantum processes that came before. For generations, physicists have searched for the so-called theory of everything, one single equation to unite all the forces of nature. But perhaps the answer is not a neat formula. Perhaps what we truly need is a shift in perspective, a new way to see the universe not as a place ruled by forces, but as a living process emerging from the quantum mist. A universe where beginnings are illusions, where gravity is not a master law but a shadow of something more fundamental. For many decades, astronomers have relied on a powerful idea called the Standard Model of Cosmology, also known as lambda-cold dark matter, or simply LCDM. This model has been like a guiding map, helping us understand the history and structure of the universe. According to it, everything began with the Big Bang, a single fiery event that brought space, time, matter, and energy into existence. The Standard Model does more than just describe the birth of the universe. It also explains the sudden burst of growth in the earliest moments known as inflation. It accounts for the faint glow we can still see today, the cosmic microwave background radiation, which is the oldest light in the universe. It also sketches out how galaxies spread through space and how the invisible but powerful ingredients, dark matter and dark energy, shape the cosmos. For a long time, this model seemed elegant and dependable. It passed many tests and survived countless challenges. Scientists praised it for being a neat fit, even though it was built like a patchwork quilt, observations and assumptions stitched together into a single story. It assumed that, on very large scales, space-time is smooth and uniform. It assumed that gravity is the main architect of cosmic structure. It assumed that redshift, the stretching of a light, is a reliable measure of distance and time. But the model has always carried with it deep mysteries. What exactly is dark matter? Why is dark energy speeding up the universe's expansion? And perhaps the biggest puzzle of all, what happened before inflation began? The model worked, but only by asking us to believe in things we could not see, define, or fully test. Now, with new eyes on the universe, especially the James Webb Space Telescope, cracks are starting to appear. Webb has found galaxies that are far too old, too massive, and too well structured to exist so soon after the beginning. According to the Standard Model, the early universe should have been a chaotic sea of particles slowly cooling down, needing hundreds of millions or even billions of years before galaxies could grow into organized shapes. Yet Webb is spotting galaxies just 200 to 300 million years after the supposed birth of the cosmos, galaxies that look far too mature for such a young universe. This is not just a small error, it is a serious break. If these galaxies truly exist that early, then the timeline of the Standard Model is wrong. It is as if the blueprints of the universe's construction are being read upside down. The equations that guided us here may have never been meant to explain this part of reality. Even more unsettling is another growing conflict, the Hubble tension. The Hubble constant is a number that measures how fast the universe is expanding. But when scientists measure it using the early universe, such as the cosmic microwave background, they get one answer. When they measure it using nearby galaxies, including those now revealed by Webb, they get another. The gap between these answers is not shrinking, it is widening. This hints that we may not even be measuring the same universe at all. These problems cut to the very heart of the Standard Model. If galaxies can form faster than expected, if time behaves differently, or if redshift cannot always be trusted as a cosmic clock, then the foundations of LCDM are shaking. Many scientists are beginning to take notice. Some now suggest that Webb's discoveries may force us to invent an entirely new theory of the universe, not just a patch or a fix, but a fresh framework built from the ground up. Such a theory might move beyond the old picture where dark matter and Einstein's general relativity are the only rulers of cosmic law. Instead, it could point towards something deeper, perhaps quantum information, or an emergent space-time, or even physical principles we have not yet imagined. Others argue we may need to look at our old data in new ways. Perhaps our predictions were mistaken. Maybe the cosmic microwave background, once thought to be the clearest photograph of the early universe, is being misread. Perhaps dark matter is not a particle at all, but a field, or the shadow of forces we do not yet understand. Perhaps dark energy is not really pushing the universe outward. Maybe space itself is changing in ways our minds have not yet conceived. This is not a failure of science. It is science at its best. Real science does not cling blindly to old maps. It questions, it doubts, it wrestles with the unknown. The Standard Model served us well. It gave us a story of cosmic order, helped us trace galaxies, and even guided us to the moon and beyond. But scientific models are not eternal truths. They are tools, and when tools no longer fit the job, they must be reshaped or replaced. Now we stand at the edge of a new cosmic chapter. The old story brought us this far, but the universe itself is telling us that it is time to write another. Those who defend the Big Bang and the Standard Model of cosmology are not just clinging to a random idea. To them, the Big Bang is much more than a theory. It is a carefully tested framework that has survived some of the most difficult trials in all of science. It has been challenged again and again, yet it continues to stand strong. The tests it passed were not simple ones, but the very core of what makes science work: prediction, observation, and repeatability. Long before astronomers had the instruments to see it, the Standard Model predicted the faint glow of the cosmic microwave background, the leftover radiation from the birth of the universe. When that glow was discovered in the 1960s, it was like finding a hidden signature on the universe itself, and it gave the Big Bang a major victory. The model also explained why the early universe contained exactly the right amounts of light elements, such as hydrogen and helium. It accounted for the steady expansion of space, the way galaxies gathered into immense structures, and even the vast empty regions known as cosmic voids. These were not small or accidental successes. They were monumental achievements, reasons why the Standard Model was crowned as the ruling explanation of how the cosmos came to be. So when the James Webb Space Telescope recently revealed galaxies that looked far more mature than expected, or black holes that seemed to have formed almost impossibly quickly, the loyalists did not panic. They did not abandon their model. Instead, they sharpened their tools. They studied the details, adjusted the parameters, and explored the edges of their existing theories. One common defense is that Webb may not be showing us the average galaxy at a certain distance, but rather the rare and unusual ones, those exceptional outliers that formed earlier or grew faster than normal. Another possibility is that Webb's powerful infrared eyes are naturally biased, picking up only the brightest and densest galaxies because those are the easiest to detect. As Webb gathers more data, including dimmer and more ordinary galaxies, the strange picture might begin to look more familiar, dissolving the anomaly into a smoother cosmic pattern. Other explanations involve the universe itself playing tricks on us. Dust, clouds of material, and even the bending of light by gravity between us and those distant galaxies could be making them look older, larger, or more organized than they truly are. In this view, the problem may not be with the Standard Model at all, but with how we are reading the cosmic signs. Supporters also remind us of something practical. Even if the model has rough edges, it is still the best framework we have to study and understand the universe. It does not need to be thrown away completely. It can be refined. Perhaps new types of dark matter will be added, or better versions of inflationary theory, or even processes from the earliest cosmic explosions that we do not yet understand. They compare this to the history of physics. Isaac Newton's laws were not destroyed by Einstein's relativity. Instead, they were folded into a bigger, deeper picture. Another point made by the loyalists is the danger of anomaly hunting, the temptation to grab hold of every unexplained observation and build an entirely new theory around it. They argue that anomalies are nothing new. The history of cosmology is full of them, and most were eventually explained within the standard model once more data arrived. As one cosmologist put it, science does not move forward on excitement alone. It moves when consistency breaks across the entire board. That breaking point, they say, has not yet happened. This stance is not without merit. True paradigm shifts in science are rare. They only come when no amount of adjustment can reconcile the old model with new discoveries. As of now, most of Webb's surprising results, while shocking, have not reached that level. To Big Bang loyalists, the burden of proof still lies with those who challenge the model. Yet perhaps the most admirable quality of these defenders is not their devotion to the Big Bang itself, but their devotion to the scientific method. They know that science demands skepticism, not only of new ideas, but also of our own assumptions. It is easy to fall in love with the dream of a revolution. It is far harder to hold the line and wait until the evidence is truly airtight. Still, even the most committed supporters are beginning to admit that changes may be on the horizon. Not many people deny that Webb has revealed something strange. Most agree that new information is coming, whether it is a deeper understanding of how stars are born, a new way of looking at redshift, or even the first cracks in a theory once thought unbreakable. In the end, the loyalty is not to the Big Bang itself, but to the method of science. The Big Bang remains the default story because for now it works. But if the day comes when the evidence says otherwise, even the most devoted defenders know what they must do. Science always bows to the truth, no matter how difficult it is to let go of the old story. Radical new models of the universe are being suggested. Science does not collapse when old ideas start to wobble. Instead, it adapts and grows. Ever since the James Webb Space Telescope uncovered surprising discoveries that seem to challenge almost everything we thought we knew about the cosmos, a quiet but steadily growing revolution has begun in theoretical physics. More and more cosmologists are turning to bold new models of the universe, models that rewrite the rules right from the very beginning of time. For many years, these models were seen as fringe ideas, pushed to the edges because they clashed with the well-established story of the universe's history. But today, they are gaining attention. Among the most discussed is the Big Bounce model. Unlike the traditional Big Bang picture of a single explosive birth, the Big Bounce suggests that our universe is just the newest chapter in an endless cycle. According to this view, the cosmos expands, then collapses, and then rebounds into a fresh beginning, repeating this process through infinite time. From this perspective, the ultra-early galaxies seen by James Webb are not too early at all. Instead, they are leftovers, survivors from the final moments of a previous cosmic cycle. Gravity squeezes the universe down until it cannot shrink any further, and then the great rebound begins. There is no absolute beginning, only transformation from one stage to another. One of the most remarkable voices in this field is Roger Penrose, a Nobel Prize-winning physicist and one of the most brilliant thinkers of modern science. He developed a theory called conformal cyclic cosmology, or CCC. This model says that the start of a new universe looks exactly the same as the end of the old one. Why? Because as the old universe keeps expanding, it stretches so far that all matter breaks down into weightless particles. At that point, the old universe can smoothly give way to the new without any fiery explosion. According to this idea, the strange patterns James Webb sees in the early cosmos may be ghostly information leaking through from a previous age of the universe. Other scientists are focusing on emergent space-time models. These claim that space and time are not the most basic ingredients of reality. Instead, they are born out of networks of quantum information. In other words, the universe works like a vast computer program. Entanglement and the flow of information create what we experience as distance, time, and even gravity. In this view, it is not that the timeline of the universe is broken, it is that our human sense of time has been misleading us. Some versions of this theory even suggest that space-time appeared all at once, like turning on a video game, which could explain why the early universe already looks mature and structured. In the more daring corners of research, we find theories like plasma cosmology. This approach rejects the idea that the universe is expanding at all. Instead, it says the cosmos is an immense and stable structure, shaped mainly by electromagnetic forces, not by gravity and mysterious dark energy. In this model, redshift, the stretching of light, is not caused by galaxies moving away, but by light slowly losing energy as it travels through the thin material between galaxies. This tired light idea was dismissed long ago, but it has found new life because Webb's results challenge the usual expansion story. Another striking idea is the holographic universe. This comes from string theory and black hole physics. It proposes that everything we see as three-dimensional is actually encoded on a two-dimensional surface, like a cosmic screen. Our universe is not really expanding in space, it is unfolding from a boundary of quantum data. In this vision, the fact that early galaxies appear already well-formed is not a mistake. It is simply how information unfolds across the holographic surface. Some scientists are going even further, questioning the sacred constants of nature itself. They wonder if things like the speed of light or the strength of gravity might have changed over cosmic time. If these values were even slightly different in the distant past, then the universe would have evolved in ways that look very strange to us today. What we see as anomalies could actually be evidence of a universe that once followed different rules. Others take the multiverse seriously, the idea that our universe is just one bubble in an endless froth of realities. In this picture, our patch of space might simply reflect unusual starting conditions. What seems impossible here might be common somewhere else. In such models, early galaxies, odd redshifts, and stars that appear too mature are not failures of cosmic law, but features of our own small corner of the multiverse. These ideas may not share the same structure, but they all carry the same spirit: cosmic humility, the recognition that the universe is under no obligation to behave the way we expect. To truly understand it, we must sometimes set aside old assumptions and learn to see with fresh eyes. Of course, radical models come with risks. They are often messy, harder to test, and quickly dismissed as speculation. They lack the elegance of older theories, but they also expand the conversation. They give us new tools, new mathematics, and new ways to approach puzzles that have haunted physics for decades. And in the end, even the wildest ideas can open doors to truths that we could never have reached by staying inside the walls of tradition.